So, I don't know if I'm sharing now again. Okay. So minimum distance classifier, I guess. Oh, the other thing I must say is that I'm going to be asking a lot because it's the only way for me to know that you are really understanding what I'm talking about, especially now that we're doing this online. I can't assess your faces, which is usually the number one variable that will tell me whether you are really understanding what I'm saying or not. So please, again, do ask, and please don't be afraid of unmute yourself and answer if I ask questions. So for example, let's try that. So if I say that on the left most rectangle here or column, how many groups do you see here? The answer would be
3.
2. And in the second one, the answer would be
2.
And in the third one, the answer would be
3.
Could be 3. Yeah. So again, it depends. So if you think about it, what you guys did here, of course, you didn't do it. How you say, you didn't purposefully process this information in this way. You just, at a glance, you naturally came to see 3, 2, and 3 again here on the last one. But actually, what you did is you actually extracted some feature from these images. In this case, for example, in the first case would be perhaps the distance between the lines. On the second one will be the orientation of the lines. And the third one, maybe it's just the distance between these dots as well. Or maybe you could have said 4 here as well if you look at this, or maybe 5 even. Look at the size of the dots instead. But the key thing here is that you actually extracted a value from these images and then use that, and then what you cluster, again, cluster analysis, or what you classify was the distance, or how that, yeah, how those features, or how that value group together. So again, here we're going to look into, we're basically going to formalize that a little bit more, and just look at minimum distance to the mean, nearest classifier, k nearest neighbor, and then look at some different distance metrics. And again,
there is some background noise which is coming. Can someone go on mute?
Yeah, sorry, give me a second, please. Estoy dando clase y estás hablando súper alto y me acaban de decir los alumnos que no me entienden porque se te oye de fondo.
You just muted yourself, Marcus.
Can you hear me now?
Yeah.
Okay. And you said the same. Okay. So I hope that's better now. Sorry, there is someone else. I'm sharing office. Two meetings at the same time. So yes, so the objective for is from this will be for you to understand again the basis of minimum distance classifier, although as I said, you probably already do, and then learn to use distance classifiers. So so basically, what we are doing here is assigning new samples to the closest class. But the question is closest to what? Because as I said, depending on how you look at this, then you may actually come up with different solutions. A clear example would be the last one, right? It's closest to what? And then also the way you group all these features will also affect your results. So for example, the first one where we look here at would be the minimum distance to the mean. So in this case, we have a bunch of points with different colors, And what we do is we calculate the mean across all these, and then look at the distance from a testing point to a new point to each of these means. So again, this is very, very, very simple, right? I only need to keep one value per class, which is the mean point. And then I only need to run one comparison per class, right? To calculate the distance from the test sample to that class, and then just choose the minimum one, right? But there are disadvantages to this as well. First is that it's very...
So Marcus, before you proceed, like the 0.3. So where does this 0.3 come from? Like, is it mean of...
Say again? Sorry.
So there is an 0.3, like yellow color point for 3. Like I was asking, where did this point come? Number 3 in the slide.
Number 3, this one here.
Yes.
No, okay, yeah. So these are just testing points. Sorry. So each of these points are testing points. The reason why they have numbers is because now I can tell you, okay, to which class will you assign 0.1, to which class will you assign 0.2, and to which class will you assign 0.3. Okay, they don't mean anything. So basically, each of the colors except the yellow one represent a class, and then the yellow one is just a testing sample. Yeah, sorry, I should have explained the legend a little bit further. So I was saying these as some.
So they are randomly. You put them randomly. There is
yeah. They don't mean anything. Points. No.
Okay. Yeah. So what are the criteria to say you will let an system to decide those 3 random points, or you give that input to decide those 3 random points?
Okay, no. So this is just an example. It's a made up example. So what you will get, okay, so let me maybe take a step back. So what you will get is you will get a data set of samples. That will be your training samples, right? So in this case, each of the colors except the yellow one will be points in your training sample. And each of the colors except the yellow one will be, each of the colors represent a different class. Okay, in this case, it has water, urban, forest, crop, soil, or ether. The yellow points now are points that your model hasn't seen before, and points that you want to know to which class do they belong. So then I just have another reading from whatever. So in this case, this example comes from, based on the labels, basically you can guess that you're trying to identify maybe in a satellite image, what are you looking at? Is this part of the land water? Is it urban? Is it forest, etc., right? So let's say that now you get another picture, you want to know one point in that picture, what is that point? So is it water, is it urban, is it forest? So this is what you're doing here. So then when you get that point, whatever features you're measuring from that point, they will fall perhaps into one of these yellow points. Okay, so this again is just made up. Well, it's
sure. No, got it.
Okay. So so yes, as I said, the minimum distance to the mean would be very simple, but then if you think about it, it's very insensitive to the shape of how your cluster, how your points, or how your classes are clustering, right? Sorry, how your points are clustering, how your samples are clustering. So, and then in the extreme, it's actually completely insensitive to clusters within clusters. So let's say, let me see if I can draw here. in red, for example. So let's say that you have these samples. You see what I'm drawing, right?
We see your pointer, but we don't see no lines.
No. Okay. So, right. So you don't see anything that I'm okay. Yeah. Fix it. Can you see now?
Yeah, that's
Yes.
better.
Okay, cool. So let's say that you have trying to do points, believe it or not. So you have all these samples, right? And then you also have these samples in yellow. So now if we're doing distance to the mean, where is the mean? So the mean of the yellow class will be somewhere around here, right? The central point. But the problem is that the mean of the red class will probably be somewhere around here as well. Can you see the problem? So clusters within clusters, completely oblivious to it. Yep.
Yeah.
Yep.
So there is another option, which is using a nearest classifier. So in this case, instead of looking at just the mean point, you're going to look at the distance to each of the points that form your class. So in this example, we have three classes: green, red, and blue. And basically, so each of the points here, so you see how now we have very funny shapes, and in fact, we even have points. Let me see if I can zoom. Actually, you can see what I'm doing. So there you go. So in fact, we even have like isolated samples here. So the reason is because now all we are doing is just assigning a testing, so a new sample that we want to test. We will assign the class of the point of the sample that is nearest to it. Okay, so for example, if I am querying what's the class for this circle here, the answer will be red, or the star, because that's the closest point. All the points of all the samples here, the closest to this one is a star, is a red point. So that's why I assigned to it that class. Okay, and the areas painted with the different colors correspond to like the boundary areas. So if you look at any point within the red area, the closest of all these samples to that point will be a star or a red point. Yes, and that's why you have here isolated points, because here there is an outlier, which is a circle or a red or a green, sorry, sample, and that means that point very close to this one will be assigned to the green class. Yes? So now again, this is again super simple. It's also super versatile, because as we see it can accommodate very complex boundaries, okay, between classes, very complex. And it will work perfectly fine with clusters within clusters, which is what we saw before. But then it's computationally expensive, because now you have to calculate for each sample. You need to calculate the distance to each and every one of the points that you use for training. Okay, So if your training data set has only, I don't know, 100 or 200 samples, maybe that's not too bad. But if you're looking at thousands and thousands of samples, then you may start getting into trouble, okay? And then actually it's now is not just sensitive to outliers, it's hypersensitive. So if you were looking at this, are you actually happy? If I ask you, are you actually happy about these areas here being very isolated?
No. I was about to ask that question. Like, if the point, let's say, is in between those, then where would you classify? Whether you classify it to green one or the red one?
Yeah, exactly. So this is actually, this will depend on your application or on your problem, but generally speaking, you're probably always going to be dealing with outliers, right? And this is basically a perfect definition of an outlier. So you have a sample that is clearly outside the area where all the other samples from that class fall, and but it's having a huge impact on how the model performs. So probably you want to ignore this class. Sorry, to ignore this sample here. Yeah, so there will be ways around this. You could identify and remove outliers beforehand, blah, blah, blah. But let's forget about that. We're talking about how the model performs against outliers, and in this case, not very well. Okay, so the difference between these two, here you are calculating the distance to the mean point where all the samples from that class fall. Here you're calculating the distance to each and every one of the samples that you use to train your model. Yes? Now, I think the last one we're going to look at is the k nearest neighbor. And in this case, it's basically the same as before, but instead of basing our decision on the class of the sample that is closest to my testing sample, I'm going to look at multiple points. Okay, I'm not going to look at the one with the minimum distance. I'm going to look at the 2, 3, 4, 5 with the smaller distance, the smallest distance. And then I'm going to base, it's like a voting thing. I'm going to base my decision on that. So I'm going to say, okay, if I'm looking at 5 and 3 out of 5 are red, then I'm going to say that my testing sample belongs to the red. Yes? So in this case, there are 2 examples, and you can see how this affects the model. So in the left panel, basically we have a nearest classifier, right? So I'm only looking at the nearest point, but here I'm looking at 5. Now you see how these green dots now, for example, this one here as well, they are not having that huge impact, and even this blue as well. So they're outliers now. They don't have such a big impact on how the model performs. Again, there is no, this is just a number, right? 5. You can, in theory, in practice, you would try different values, see which one works best for your problem at hand. But you also see here some white areas. What do you think these white areas represent?
Unable to classify anything there?
Yeah, exactly. So these are, if you want, confusing areas or areas where you don't have a clear winner. in this, yeah. So in this case, some of these will be a little bit funny because if you have, if you're looking at 5, it's a little bit harder to, it's a little bit hard to have a type, but you can still have, in this case, for example, you would probably have, if I had to guess, 2 dots that are blue and 2 dots that are red. So then you have a tie there. So if you are implementing this, you will have to think, how are you going to deal with these situations? One example would be to look at the, say, for example, if I don't have a clear winner, then I'm going to choose one at random. That's an option. Another option will be actually, I don't want to give an outcome if I'm not sure about it. Any other possible solutions to this that you can find? The reason why I'm asking is because this will tell me whether you guys are understanding the concept as well.
No. Then I would prefer going with this model where I can get some kind of answer rather than going with 5 and then, because when I see there is a lot of white area, which tells that many of times I don't get any match.
Okay, but let's say that you want to give an outcome always. You have that requirement. You have to give an outcome always, regardless whether you are on a kind of like a confusion area there. You need to pick something.
Could you just class it as an uncertain class?
You could do that as well. The other thing that you could do is that instead of just saying, oh, I'm going to look at, instead of just saying, oh, I have 2 that are red and 2 that are blue, I don't know what to do, you can also calculate like a weighted distance if you want, or a weighted mean or something like that. So for example, you can weight how much each sample or each class weights towards the final decision based on the distance of the points of each of that class. So for example, if I have, okay, I have 2 blue and 2 red, but the 2 blue ones are really, really, really close or closer to the sample than the red ones. So then I may decide, okay, my guess then is that it's going to be belong to the blue class. Yep. So these are just different ways that you can think of and solve this issue. Finally, well, almost finally, we have different metrics. So far, so far we have been using inadvertently what is called the Euclidean distance, which is, you know, when I tell you what is the distance between these 2 points, then you just draw a straight line between the 2 points and then measure that line somehow. Yes. There are other ways of measuring distance. These are 2 examples. You have the Manhattan distance. So that will be, imagine that your dots lie always in the intersection of a grid like this one here. And now the Manhattan distance is how many steps you have to take to get from A to B. So for example, if I am, go here, it's clear. So if I am here and I want to get to here, so what the solution would be in Manhattan distance. What is the Manhattan distance, sorry, between these 2 points? This and that.
2, 2, is it?
2, 2 or 4, which is what you would,
Okay.
the Manhattan, yes, 2, 2, that's fine, but it's 4 also because
You add them up.
well, no, yeah, you basically add them up. So it's 1, 2, 3, 4. And if you look at it, it doesn't really matter which path you take, that the shortest one is always going to be 4. So 1, 2, 3, 4, 1, 2, 3, 4, so on and so forth. Of course, if you wander around, then you will have longer distances, but we're always talking about the closest one. And then the Mahalanobis distance here, which is the one that is widely used, really, is takes into account how the samples, all classes, distribute in the space. Okay, so in this case, in this image, let's zoom in so that we focus on this. You see how this axis, let me draw, so this axis 1, for example, here, compared to the other axis, axis 2, is kind of like a squashed, right? So at distance, the 2 points that are, let's say, 2 points that are this far away, in the first, in axis 1, will be farther away, if you think about it, that 2 points, or the distance it's not that they are farther away, is that they cover more ground in terms of information. So if we're thinking about this, so basically think about the range of two numbers. That would be a good way. So the range between two numbers. So if I tell you that there is a value that can go between 0 and 10, and then it tells you that there are 2 points there that have a distance of 5, that covers 50% of your range. But if that value, if the range goes between 0 and 100 instead, then that distance is only 5%. So that's basically what the Mahalanobis distance is trying to normalize. So what the Mahalanobis distance does is basically make it so that the range of each dimension is always 1. So then you're always measuring, when you're calculating distances, you're always measuring you're making sure that you are comparing like to like, if you want. Let me see, how can I explain this to you? Well, explain why this is important. The reason why this is important is if you are looking at, if we were using the Euclidean distance, okay, let's say that the distance in the first axis here is 0, okay. So let's say we're looking at 1, 2, okay. Sorry for my beautiful drawing here. So in the first example, the distance in axis Y is 5, and the distance in the axis 2 is 0. And in the second case is the other way around, 0 and 5. Okay, which of these two distances do you think is shorter? Or do you think they are both the same?
Which one is what, sorry?
Which one is short? So which one is a shorter distance?
I would say 5, 0 is shorter distance.
You think 5, 0 is a shorter distance? Yeah. Anyone else?
Yeah, same.
Okay. So actually, okay, so if we were looking at the Euclidean distance, okay, then these two will be the same, right? Now, in this case, if we're looking at the Mahalanobis distance, 5 to 0, if we say that this goes, that one goes between 0 and 10, so basically shorter, which is what we have here, 1 is shorter than 2, then this covers 50% of the whole range. Whereas this one, if it goes, let's say this is 0 and 100, then the second one covers 5%. So actually, the first distance is longer than the second one, because when you travel, we're talking a little bit sillily here in terms of, the work we're choosing, but just so that we understand each other, if we travel a value of 5 in this direction, we are crossing so many lines here, right? So we're covering a lot of the distance, a lot of the range of this axis. Whereas in the second case, if we travel a distance of 5, then we actually cover less space in total, less of the range. So that's why the first distance here is actually larger than the second distance. Do you understand this?
No.
Okay.
Where does I think I get it, but where does it come from, these axes? Is this sort of normalized on the data you got? Is that what determines this sort of grid?
Yes, exactly. So basically, yeah, exactly. You will be looking at, so these two axes may be 2 factors, for example. And then again, in this case, you will be looking at, so depending. So this is example, maybe this is not the clearest image to use. A clearer one will be one where the axis 1 and 2 will perfectly align with X and Y, right? But if you have you heard of, I don't know if they have, Aaron, about principal component analysis, PCA?
We briefly talked about it earlier, yeah.
Okay, cool. So basically, if you apply PCA here, this is the 2 axes that you will find. Okay, so you will find the axis where the dispersion is greatest, and they are perpendicular to each other. Perpendicular. Yes. So this is what these 2 axes represent. But what these 2 axes are kind of like less important to understand the concept, although they are, which these 2 axes are, is actually really important when you're going to apply the Mahalanobis distance. But what I need you to understand is the fact that one feature, one value that you're going to base your metric on may go from 0 to 1, and another one may go from 0 to 100. Another example will be, for example, if you're going to differentiate between, let's say, basketball players, right? So then you're going to use now, let's say, 2 metrics, weight and height. So, of course, height will go from not even 0, because that wouldn't make any sense. But let's say if we're talking about meters, I don't know, maybe 150, that would be a very, very short basketball player, to, I don't know, to whatever. I don't know what the tallest basketball player is, but let's say 220, I don't know. Whereas if we're talking about weight in kilograms, then maybe we are talking between 60K to, I don't know, 130, 140. Yes. So now, of course, these two measures have very different nature, and they are very different to each other, and their ranges are very different. So a distance of 1 kilogram is nothing, whereas a distance of a difference of 1 kilogram between 2 players is not really that much, whereas a difference of 1 meter between 2 players, that's a lot. Yes, so that's where the Mahalanobis comes into play. So basically, what you do is you transform these values, so you adjust them so that now they all go between -1 and 1, for example. Right? That's what you usually do. You make them 0 mean and standard deviation equals to 1, variance equals to 1. Okay? Is it clearer now?
Yes. So basically, you are saying that we would convert those two into an, what you say, comparable scale.
Yeah.
By applying Mahalanobis distance value. Okay.
Yeah, exactly. Yes.
So is there any mathematical formula for it?
Yeah. So basically, again, because I didn't want, so all I want for you guys is to understand the concept. I don't have any maths in here because usually if I put math, it tends to scare people, particularly when we get into neural networks. I have tried to keep it to a minimum.
Sure. Got it.
But yeah, but if you, this is a very, very well-known, Mahalanobis distance. If you look it up, you will find like a gazillion pages telling you what the equation is. So just to wrap it up, some pros and cons of the distance-based classifiers. They are very simple, very intuitive, right? They may start getting more complicated when you start using different metrics. There can be other metrics apart from this, okay? The ones we have seen here. But the main concept is very, very simple. There are very few parameters to optimize. So now we have talked about if you use k nearest neighbor, you have to optimize k. You have to optimize maybe even the distance that you use. And it can implement, it's very versatile, right? So you can implement very complex class boundaries. Basically, it adapts very well to very weird shapes. However, it can be very, very sensitive to all layers. It's super memory hungry and it's super computationally expensive. Okay, particularly when you start using more fancier distances, which is actually quite interesting to do. In any real world application that you can think of, the Euclidean distance probably won't cut it because of what we said, right? Look at the clear example, the very quick example we discussed about just differentiating between basketball players. It was very easy to find two metrics that are actually quite different between each other. Okay, so usually we will do some Blackboard exercises first, but because we don't have much time this year, and because, again, this usually is pretty straightforward, people understand it pretty quickly. The second exercise is usually to write a distance classifier yourself in R. But instead of doing that, based on some input from students from other years, we're just going to go through the code that I have here. Let's
just to say, Marcos, I've put the scripts now up on the Kaggle resource. So for those of you that would prefer to use Kaggle, yeah, this notebook is on there. It's the minimum distance classifiers. Just make sure you refresh the front page on Kaggle, and you can follow along that way if you want to.
Okay, thank you. Thank you. So very, very quickly, we're going to use this breast cancer Wisconsin data. So it's just a data set that is publicly available. Anyway, all these files are, I guess, as well as in, what was the name, Cargo, where Aaron just said. They are also available in Canvas for you to download. Just to have a quick look at what we have here. So basically, this is a data set with different, so we have samples from different people measuring different factors, clamp thickness, uniformity, cell size. I'm not an expert in this, but factors that are in principle interesting to identify whether a cancer is benign or malignant. You can also look, so basically we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different factors. The first column is the person ID. That's not really interesting for us. And the last column is the class, so whether it's benign or malignant. Yeah. Then you can also look at what each of these features, if you want, or columns, what kind of class they are. So these are all integers really, and the last one is string. You can look at how many levels, in this case, only the last one, the class has only 2, benign and malignant, and then just the dimension, we have 683 samples and 11 columns. Okay, so just a word here. So when we look at this, in machine learning terminology, we will be talking about features. In healthcare, probably we're talking about factors, risk factors usually, or protective factors. Those are the ones that we are going to use to guess our outcome. If we're talking in machine learning terminology, that would probably be the output more than the outcome, but they are all the same, right? So we have variables, features and factors, they are this, yes, features and risk or protective factors, they are the same. And then we have the output class or the outcome, they are both the same thing as well. You can also plot some of these. This is just to show, to have a quick look at the data, that you know what we're doing or what we're dealing with. Here we see how each feature plots against the other one. So it's 2 by 2. That's why we have so many. So the first one is mitosis, normal nuclei, and then because it runs down. So this is a square matrix. That's why the diagonal is empty, which is because it doesn't make sense to plot mitosis against mitosis, right? Okay. Another plot. And sorry, and the reason why this is interesting is because you can see a little bit how these, you know, it tells you a little bit how combinations of 2 features can help you identify between the 2 classes, right? The blue and the pink one. Yeah, so you see how, and you also see here how they are distributed. So these lines that you can see here, they are kind of akin to, or similar to what we were discussing about the Mahalanobis distance, right? You see how they distribute across the range. And you also see here different ranges, right? So 2, 4, 6, but this other goes 6, 8, 10, right? So again, the values could be very different. And then the second plot. This is just a different, so now we're plotting the histogram of each class or each feature, right? So for each risk factor. And you see, you could tell, for example, this one is more or less revealing or helpful to differentiate between the 2. This one as well, you know, they are more or less by telling. This one will be the one that is less or the least helpful, right? Because they have the peak exactly at the same point. Although you can extract some information here because the tail is longer, right? Anyway, this is just to have a quick look. It's good to have a quick look at your data before proceeding. So let's see this. I'm going to zoom in, and again, I'm going to go quickly through this, but it's just to show you that what we were saying before about this being really, really simple to do, right? So we read the data set, blah, blah, blah. We split the data into training and testing, blah. You can look at these later, not really important for what we're talking about. This is pretty generic. But now we're going to write a function that trains a distance metric model, right? So the input, so we have 4 inputs. The first one is a matrix containing the training data. The second one is a vector containing the training labels, right? Benign or malign. K will be this K nearest neighbor, what value of K we're going to use, and then the type of metric we're going to use, which in this case, I think I only wrote the code for the Euclidean one for this example. So basically, if you look at what this is doing, it's not doing anything at all. Literally, it's just taking the inputs and saving them in a structure. That's all it's doing. I'm not doing any computation whatsoever. And this is my training function. I don't need to do anything, okay? Now, it's when we're testing, when we have to do stuff, okay? And this is now a key quality of these models, which is they are very extremely quick to train, time consuming for testing. Now, if you think about applications, you don't train your model every second. You don't train your model probably not even every day. But you're probably testing samples against your model maybe every second, depending on your application, right? So in the health context, if this is let's say that your model, you're trying to say whether, again, this example that we're looking at, you're trying to differentiate between malign and, I don't know how you say, malignant, how you say malignant and benign cancers, breast cancers, you're probably going to have clinicians using this model continuously every day. But you're not going to retrain that model every day. You maybe retrain it every week, every month, depending on how much data you are producing. So the training time is not always the critical time for your model, right? Anyway, so now if we go here to how we test, my testing function has 2 input arguments, the model, which is the outcome of my training function, and then X, just a matrix containing the testing data, right? So the first thing I have to do is create a distance matrix. And the size of this matrix is equal to the number of samples I have for testing and the numbers of samples I have for training. And this already tells you that this is going to be super memory hungry. Because imagine that you have million training samples, and now you're going to test 10 samples against your model. Now you need to create just the first thing you need to do is to create a matrix that is 10 times a million. I mean, you could tell me, yes, you could optimize this and then do it individually for each sample. But you will still need a vector of length 1 million. You also need to keep a record of the indices of the closest samples. So for each sample, you're going to have K closest other samples, right, from your training set, because we're using the K nearest neighbor, and K is just a parameter. It could be 1, 2, 3, 4, 10, whatever. And you're also going to record the distance, okay? And then you're going to go, this is a nested loop. You're going to go through each of your testing samples, and for each of your testing samples, you're going to go through each of your training samples. And then again, you can say, yes, Marcos, but you could optimize this and use matrix operations, blah, blah, blah. Fine, yes. But this is just to illustrate what we were saying before about this is computational intensive as well. So you have to go through each of the samples. So each pair of testing training sample, you have to go through each of them, calculate the metric, in this case, the Euclidean distance. We save it in the distance matrix. Then we find the k closest ones. And then we calculate kind of like the probability based on this, right? So basically we say, okay, if we have 5 out of 10 are from class, sorry, if 5 or 8 out of 10, if we're using k equals 10, 8 out of 10 belongs to the benign class, then we say there is an 80% probability that this class belongs, is a benign, this sample is a benign cancer. Yes? So that's what we're doing. So if we run this, so this just defines, so again, what we said before, training, super quickly. You see that? And look at how long it takes to test. Still thinking, still thinking, still thinking, and still thinking. Okay? And this is with a sample of how many we said? 683 points? Sorry, data set. We're using, I think we're using 10% for training. Yeah, the split. We're using 10% for training and the rest testing. So it's still thinking. I mean, as I said, yes, this is super inefficient code, but it's just an illustration. If you were to run, well, no, I guess you could use libraries. I was going to say, if you were to run this on C or C++, it will run faster, but but unless you use specific mathematical libraries, which you will have to do it like this. MATLAB, for example, is already optimized for matrix operations. Then we just compare our results with the true labels or the true outcomes of the testing samples, and we get a success rate of 96%, 95.9%. Okay. Anyway, you can go through the code on your own and look at how I have done it. Again, I don't claim this is neither the only solution nor the best, but it's a good, I hope it's a good illustration of how distance-based classifiers work. Again, you will add, this is just to show that you could add here other types of metrics. Yeah. Any questions about this? Ooh. That's okay. I think we can stop later. Yes. So I think what we can do now then is jump into the neural networks. After the break, then probably we can do the exercises. I don't think we will have time to do that. So anyway, any questions about the distance-based classifiers?
Do you know what you just went through there? I'm guessing you're just kind of showing how it works, like behind the scenes. But in reality, there's functions out there that do all that kind of thing.
Absolutely.
Yeah.
100%.
Okay. Cool.
Yes. So the reason why, so basically, this is based on students' feedback saying that it would be good for them to understand is exactly what you said, to understand better the behind the scenes. And we kind of did also for the neural networks, it's a little bit more complicated. The code is a little bit more elaborated than what we have just seen, but I think it helps to get the basis. I agree with that. And I hope it does help you as well. So any other questions or comments? No? Okay, so let's jump into artificial neural. Yeah, sorry?
Well, Marcos, I was just wondering, would it be a good time to have a quick 5-minute break, or?
So how many, do we have one break for the whole afternoon or two?
Up to you guys, how you want to plan it. I was just thinking, we've been working for an hour now.
Okay, let's stop for 5 minutes. So I'll see you guys at 2:05. Is that okay? 2. Have you heard the expression? Have you heard people referring to them as black boxes? Well, probably. Okay. Okay, fine. So what we're going to see here is we're going to try to, okay. So usually when they say black box, that an artificial neural network is a black box, that we don't really know what's going on behind the scenes. That's not really true. It's not that we don't know what is going on behind the scenes. We do know pretty accurately what is going on behind the scenes. What we don't know is how to express that into a way that is manageable for us humans, right? So just to give you a very quick example, if we were talking about before we were saying about differentiating basketball players using height and weight, if I tell you that, you know, oh, I know that this basketball player is this because, you know, maybe his weight multiplied by 2.5 plus the height multiplied by 1.3, and then I apply a logistic function to this, and then I do this, and then I do that, and that's how I come up with my solution. And then you say, well, you're not really telling me much, Marcos, there. You're just telling me how you did it, but it's not really useful for me. So that is the problem we have here. But there are ways to work around that, although it's still a very hot topic in research at the moment, because probably that is where the money lies at the moment, trying to you know, find a way to properly explain or understand, more than understand, find a way to express in a humanly understandable way how a neural network is coming up with a solution or with an outcome, with an output. So we're going, yes.
So I've heard people talk about this, saying black box, and I've heard people say, oh, we don't know what it's doing. But I guess we do know what it's doing, but it's just really difficult to explain. Is that what you're saying there?
Yes, exactly.
Because it's all kind of mathematical or whatever is going on.
Yes, exactly.
So it's not that it's just doing something random that we can ever understand. We know exactly. Okay, cool.
Exactly. Yes, basically. I mean,
wait, so then how was it built?
How is it built? Yeah, so that's what we're going to look at today. So we're going to look at how artificial neural networks learn, and we're going to look at their structure, and we're going to look at how what they can do and how they learn. Okay. Yeah. So we'll get into that. So this is what we're going to, the content. We're going to talk about Perceptron first, which is basically just one neuron. Then we're going to talk about neural networks. And then we're going to talk about the steepest gradient descent, what it is. And then how do we use it in the learning algorithms, which is what we have just mentioned about how they learn, how they come out to, how they go from something random, which is when we instantiate them in the first place, they have random numbers most of the time anyway, and then how they go from random to very specific. Yeah. So again, the objective of this is for you to know the basics of artificial neural networks. So this, I think, will be the more complicated thing. From here on, if you want to go from this to learning convolutional neural networks, deep learning, other types of deep learning architectures, it should be relatively easy, okay? Because they always go to the basics. It's only different ways of applying this, or maybe doing small modifications to this to make it better, really. And we will see examples of that as well as we go along. So the perceptron, we say, is just one neuron. Basically, it's actually quite simple. It's been around for a very long time. I'm not going to say a year because I'm probably going to make it up. So, but it's been there for a very, very long time. The only reason, well, artificial neural networks have been around for a very long time. The only reason why they only became popular very recently is because of the computational power, really. So before we weren't able to do the kind of models that we have now in things like, I don't know, Siri, for example, or any of that. So this is how a perceptron looks, okay? So we have some inputs, okay? Then we have some weights. Then we add up everything together, and then we apply a function, okay? So the input is just a number. The weight is another number. We multiply the input by its weight, okay? Then we add everything together, yes? And then we apply whatever function that we have. This is called an activation function, yes? So this is what a perceptron is. And this is actually really good at classifying things that are linear, okay? They are linearly classified. That can be classified with a straight line, basically, or differentiated with a straight line. So first, it has to be trained. So the input values will be values from our training data, yeah, from our training sample. The weights at the beginning, as I said before, they tend to start as with random values, okay, or at least more or less. When I say at least more or less is because in practice, you apply some, it's not a complete randomness. You try to keep them within a certain range so that the whole thing stays stable, right? And then and these weights is they are what we call the parameters in our perceptron. Okay, so these are the values that we need to learn. So we need to learn which values should I use here in my weights, so that given the inputs that I'm going to have or that I have, at the output I have the value that I want. Okay, so that's all we want to do. So that's what we need to, and the question is, how do we find these weights in an automatic way? So as I said, the disadvantage of this is that the perceptron is that it's only capable of differentiating, solving linear problems. And I'm going to show you an example here, right? So this line is what the perceptron is doing. So everything to the left of the line is one class, everything to the right of this line is another class. So at the beginning, here is where it starts. So that's where the perceptron starts with its random weights. And then each step of the learning process, you see how this is moving to its optimal place. Yes, and then at the end is pretty good at differentiating between the two classes here, red and blue. Yeah. Okay. The learning thing, the learning algorithm is what, as I said, is what we will look at the end, because it's maybe the most complex thing. It's better to understand everything else first. So the perceptron, if we put it in mathematical form, a little bit of maths now, this is what it is. As I said before, we just have all our inputs multiplied by our weights, which are our learning parameters, the parameters that we need to learn. Then we add up all of these together, and then we apply a function. Okay, this B here, this is like a bias term. In this case, the bias is, as you see, this first input is always 1, so it's fixed. So that's our bias term. So you can do it like this, or you can just move it outside of this, add up together and weights and put it outside. But in effect, it's the same thing. Okay, it's just a term that we have. It's literally a bias. So we're moving the whole boundary up and down a constant value all the time. Okay, cool. And then this function could be almost anything you want. Okay, so these are very common activation functions. We have steps. So everything below 0 is 0. Everything above 0 is 1. We have sign. So in this case, everything below 0 is -1. Everything above 0 is 1. So that's what we're doing at the end. When I say everything, I mean when we add up together when we multiply each input by its weight and add up everything together, we look at that value and then we say, okay, if this is greater than 0, then we output 1. If this is lower than 0, we output -1 in the case of sign function. Then the linear function is just the same that goes in, goes out. Piecewise linear, blah, blah, blah. An interesting one, the logistic one, okay? The logistic one, it's interesting for many reasons, but one of the reasons why I think it's interesting is because the example of an application of this is because what you're doing is a logistic regression. So it's not doing magic. It's something that we are still doing in epidemiology, for example. We apply logistic regression all the time to find the influence, how risk factor is influencing my outcome. Okay, so it's not something that we don't use already.
Marcus, sorry, just a quick question.
Yeah.
Obviously, logistic regression, whenever you do it in an activation function, is referred to as the sigmoid for the activation and stuff like that. And then like is it the linear one? Is like the ReLU. What is usually the name that you put into the activations for these other ones, if that makes sense?
What do you mean the names?
Well, so for example, like I've done like some stuff in TensorFlow before in the past and stuff, and you obviously put for like each layer, you say what you want the activation function to be, and logistic regression tends to be referred to as sigmoid.
Yes,
I know, like, when you put in like, is it linear one, then it's like you type in, is it ReLU or something?
Okay, so you mean for each of these activation functions, which value will you have to type in?
Yeah, if that makes sense. To get...
so that will depend on the library that you're using, really. So for example, in TensorFlow, probably there is one for linear, but I don't know. But I'm just guessing because linear is it's a very basic one. I guess they have it implemented and they're using it. If you use, for example, PyTorch, so in PyTorch, you don't type it, or at least I don't use that functionality in PyTorch. you just call that function and then pass the function. And then in this case, I think for the sigmoid, maybe I think it's called sigm all the way, so without the OID.
Oh no, that's cool. So it's just because obviously some of them had like the alternative names. I was like, oh, I wonder what the if you knew what the other ones were and stuff like that. To just
oh no, this is because it can be called both things. So that's the only reason why. Yeah. But that would be very dependent on the library that you're using, really.
Okay, cool.
Just to say there, Andy, that yeah, linear and ReLU, they're distinctly different.
Yeah, no, I know it's like different, like kind of like it doesn't go 0 and then up to 0.
Yeah. Okay. Yeah. Great. Good stuff. Yeah.
Cool. Okay. The other reason why the logistic and the hyperbolic tangent are interesting is because they kind of squash everything between two values. So it doesn't matter how large or how small your input to that function is, the output is always going to be between 0 and 1 for the sigmoid and between -1 and 1 for the hyperbolic tangent. Yep. And that is interesting. Again, this is something similar to what we were talking about before in terms of the Mahalanobis distance. Okay. And it's actually a requirement that you have to do outside of the neural network. It's always better. It's a requirement if you want it to work well, let's just say. It's not that it won't run, it will run, but it won't work at its best. Or maybe it won't work at all. You need to normalize your input so that they are between whatever two values, 0 and 1 or -1 and 1 are the usual values that we use for obvious reasons in terms of, if you think about, you were learning statistics, they always said about zero normalizing stuff, set normalizing. It's just easier for when you're doing the math later. But anyway, this is just, this is just a sample of a few activation functions. There are lots and lots and lots of other activation functions. And in practice, you will basically try different ones. But then again, a lot of the time, people only use the same 2 or 3. So the logistic and the hyperbolic tangent are fairly used. But nowadays, because we have huge neural networks, a lot of people use the step function because it works relatively well. And there is one that is not here that is called the rectify linear, which is 0 below. It truncates the output to 0 when the value is below 0, is smaller than 0, and then it outputs linear when the value is greater than 0. Okay, so now we're actually going to do a perceptron manually, believe it or not. So this is what we're trying to achieve, okay? So now you have to imagine, let me see if we can do this on Zoom. This is a challenge now for everyone. Okay, so we have a 3x3 image, right? Three by 3, okay? These are my pixels. And now I say that my pixel is 1 if it's on, and then 0 if it's off. And now we want to do something to build, to find the weights of a perceptron that will help us differentiate, to identify a horizontal line or a vertical line or a cross, right? So when I say a horizontal line, it means that this is 0, this is 0, this is 0, and now I have 1, 1, 1. So sorry, a horizontal line in the middle. So say 0, 0, 0. Okay. So what I need is, let's say this. Let's call the pixels P. So this will be P11, P12, P13. Yes. So forth. P21, P2, P3. So what I want now, and actually it's probably easier if I just type. So what I want to know is, so basically what I'm going to do is P11 multiplied by W11, okay, that's the weight for this pixel, plus P12 multiply W12. Plus, so you get the idea, at the end we have P33 multiplied by W33, okay, and then you can also have a bias term, yes? So I want this to be 1 only in this case, only if I have a horizontal line. If I have anything else, I want the output to be 0, okay? So try to have a think about it. I'll give you a couple of minutes and then I'll show you, and then we'll discuss here what can be the result. Try to have a think. Have a thought.
Do you need to think about activation functions for this as well or not? As well as that equation above? Or are we going too far?
Yes, so let's use it. Yeah, thank you very much. So let's use the, let me start this. So let's, okay, now let's use the this one here, the unit step. So let's say that our activation function is, take text. I need to this out. No. Okay. Sorry, guys. Let's say that this will be, you know, whatever the output is here. Whatever the solution of this, I had, I didn't know I couldn't select afterwards. Sorry, guys. Let's say it's going to be 1 if it's greater than 1 and 0 otherwise, okay? Actually, let me share this.
So just to clarify with this then, there's no like additional steps where you to like divide things by 3. I think it's literally just doing the multiplications and it coming up to like then 1 at the end.
Yeah, exactly.
Okay, so would it be like, because there's a third, isn't it? It'd be like you times it by 0.333 recurring or whatever.
Yeah, you have to look at things like that, yeah.
And then you add them all together, because otherwise if it's the 0, 1, it'll just be 0 and then came out 0. And then is that sort of the concept you're after, or?
Yes.
Okay, cool.
I think so, yes. if you prefer, well, let's do it with the 0. This is a very ugly image. 0, 0. This is what we want to find. Just already have it there. Cool. So any ideas? Have you thought of something at least that has moved you closer to the solution? Okay, let's try some random values at first. Okay, let's say that we're going to set our weights exactly to the same values that we're trying to identify, right? So 0, 0, 0, 1, 1, 1, 0, 0, 0, right? So if we do that, then what will be the output of this if we show this? If we see this, sorry, if we see this made, this is our input, and then let's say that our weight, okay, let's call this image, let's call this weight, okay. What is the output that I get?
Is it b plus 3? A function of
yeah,
b
b exactly, yeah, b plus 3, and then we actually have to set b, let's say b equals 0, so it will be 3, right? So then 3 is greater than 1, so we have the output of 1, which is what, sorry, greater than 0, sorry. So we have the output 1, which is what we want, right? But now we need to try, or we need to think what will happen there if I have this. Now this is not a horizontal line, right? This doesn't exactly align with what we want to identify. So what is the output? So 0 plus 1 is 0. So the output is still going to be 3. Yep. So we need to change this to something else so that the output here is lower than 0. Well, can you think of anything? Any suggestions?
Negative numbers.
Negative number, yeah. Which value would you like to try?
It's going to be -3 or
Yes, okay. -3 or -4, yeah. Let's say that lower or equal to 0 is 0, okay? Just for simplicity. So then if we say that it's -3, then the output is 0. Yep. So now you have to think again what happens if we have this. And then the solution is the same. So this will work. So now if these are the weights of your perceptron, now this perceptron, and this is the bias, now this perceptron perfectly identifies, no, wait, okay, now let's think of another case. What is the output of this?
One, is it?
Yeah. So now we need to do something to our parameters, which are these, so that the output in this case is not 1, but 0 or below 0. What could that be? So the key here is in the bias, right? So if we set the bias, so the bias, you can think of the bias as a threshold in this case, if you want. So
-3 for the bias, is it?
-3 for the bias. -3 would be going just a little bit too high. It would
That's
have
too.
to be maybe 2.5.
Yeah.
Okay, because otherwise, if we set it to -3, then in this case,
You
the
wouldn't get
output,
over it.
it
Yeah.
would be zero exactly. So it will have to be -2.5, for example. That's just an example. So in this case, now it doesn't matter what you have, that is here in the image. This perceptron is only going to be 1 when we have a horizontal line. Okay. What if the perceptron that we want to build needs to identify vertical lines? And now you can think, yeah, sorry, go ahead.
Just flip your weights around.
Yeah.
Just
Exactly. You can just flip your weight around. Oops. There you go. And this will work as well. Sorry, I want to. Now, what if you want to find a cross? Or let's make this other. So we can do as we did before. We can start with the same pattern. A bias of 0, and start modifying this so that we only find this, right? So in this case, the output will be 5, right? But now, in this case, the output is still 5, and I need it to be below 0. So maybe now my weight should be -5, for example. And I do the same everywhere else as we did before. And now I have the problem that what if it's only 1 pixel here in the middle, for example, that is 1 and the others are 0, then my output is 1. So I need to set the bias so that it's only 1, so that the output is only 1 when, or greater than 0, only when I have all these pixels on. Okay, so that would be, for example, -0.5. If we do the same as we did before, right? Yep. So you see, so these are 3 perceptrons, very, 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 very simple classification models that, you know, they actually work, the way they work is quite intuitive. The only issue that we have is that, yeah, okay, Marcos, but, you know, the computer is not really doing this. It's not really going through the values and then changing this, changing that, and trying to guess and all that. And it's true. So again, the only thing that we need to now understand is, okay, how do we really get this or any other combination? This is just a solution, really. But of course, we can have many different values here. If I set this to -100, it will still work, for example. Okay. Questions?
Which bit of this? So it's a stupid question. Like, what the neural network bit of it is this related to neurons? Just
Yes.
curious.
Yes. So the neural network. Actually, let's stop sharing this and go back to the slides. The neural network, it's just a combination of perceptrons. It's just putting perceptrons together. Okay. So in a neural network, basically, with each of these circles are almost, and I tell you now why almost, are neurons, are perceptrons. So one perceptron is 1 neuron. Okay. The reason why I said almost is because usually, for some reason, I don't like this, but it's the way they do it. The first column, okay, the first layer, if you want, these are just the inputs. So it's the same as we have here, okay? Which to me is confusing. They should have a different symbol, but anyway, this is the first, this is the input, and then this is the first layer, this is the second layer, and then this is the output layer. And now in this case, the output is here. So that's why I said this is confusing. So the first column here are just the input values, and then the output values are at the end or at the output of the last column here, okay? So, and this is usually, again, the way we stack layers and the way we connect the neurons, okay? So each input value or each input feature or factor goes to each and every one of the neurons in layer number 1, okay? And then the output of each neuron in layer number 1 goes to the input of each neuron in layer number 2, and so on and so forth. Yep. Again, this is not the only way of, as you can imagine, this is not the only way of connecting layers or neurons between layers. You can have any combination you want, really, but this is like the basic one, okay? So the key here is that now, we said before that the perceptron is only capable of solving linear problems. Now, when we put perceptrons together like so, and we give the perceptron the activation function that we use is a nonlinear one, then our neural network can solve nonlinear problems, okay? So if you're bored one day and you want to play around, I'll show you, will I? No, okay. So I was thinking whether I have the equation for this. We can actually have a look at it. What happens if what you have here, what happens if the activation functions that you use are always linear? Then you end up, it doesn't matter how many perceptrons you stack up, it doesn't matter how many layers you stack up, you're always going to end up with a linear function. It's equivalent to having one neuron. So it's vital that you use a nonlinear activation function if you want to solve nonlinear problems, okay? So again, a nice example of how this works. There's another GIF here. So this is, so you see how the neural network now is step by step is creating this, is able to identify this cluster, right? So these lines are representing kind of like thresholds, if you want. Not exactly, this is basically, you have two values, 1 and -1 if you want. Let's say +1 is the yellow one, and then the more to the pink you go, the more negative you go, right? So the white dots will be represented by an output of -1, and the black dots will be represented by a value of +1. So this is similar to what we did just now with the pixels, right? So we wanted an output of 1 or -1 or 1 or 0. So you see how with every step in the learning process, it's getting closer and closer and closer to that. Okay. So you can do whatever you want really here. So you can have as many neurons as you want in each of these layers, and you can have as many layers as you want. So you have probably also heard about deep learning, okay, or deep neural network. A deep neural network is basically a network with many layers stacked, okay? The reason why that was novel or why that became popular is because someone found a way to train those networks. So there is an issue when you are training with multiple layers. There is something that's going on there that is preventing the network to learn by using the traditional learning algorithm. So they had to find a way to fix that or to modify. They have to modify that learning algorithm so that now it works with when you have multiple layers stacked. Okay. And nothing else really. So it's as simple as that, really. In the sense that all you are doing on an artificial neural network is putting multiple perceptrons together like this. So if you think about the logistic function, the logistic regression, then basically what you're doing is doing many logistic regressions, right? So you have each of these neurons will be a logistic regression, and then on the next layer, you will be doing a logistic regression with the result of all your previous logistic regressions, right? So this is actually what you're doing in that scenario.
Marcos, does each neuron just always have an output of 0 or 1? Is that how it works? They switch different combinations of these on, and then it multiplies by an activation function?
Yeah, so depending on what your activation, so depending on what your activation function is, your output may be always 0 and 1. So for example, if you're using the unit step, then the output of your neuron is always going to be 0 and 1. If you're using the sign, it's going to be -1 or 1. If you're using the linear, it could be anything. And if you're using the sigmoid, then it could be anything between 0 and 1. Yeah. Any questions? Because there is nothing else to say here unless there is some specific questions. It's really as simple as that.
Marcus, can I read you through what I've got in my notes, just so I've got it correct? I think you basically did just say it, but I want to be sure. So each perceptron takes in a number of inputs. Each input is multiplied by a weight, and each weight is unique to each input. You add a bias. You run it through an activation function, which outputs a number according to whichever function you've chosen. And then that output becomes the input for the neurons in the next layer.
Exactly. The only thing that I will tweak there is that the bias doesn't need to be unique.
Right, okay. Okay, perfect. Thank you.
Cool. So this is actually the next exercise to play with this. So I'll let you copy this and put it on your web browser if you can. And then I'll move my web browser in front so that I can show you.
Marcos, I think you can put the link in the chat.
Okay, good
Might be
idea.
a bit easier, yeah.
Thank you. Okay, so this is what you will find. So basically, this is for you to play. So if you click, if out of the box you just click play, you will see how the neural network is learning. You will see, let me pause it now. You will see this is the error or the loss, as they call it. You will see how it goes down. You will also see in the diagram or in the plot how the network is learning to differentiate between the two classes, and then you can play around. So forget about the top row here with learning rate and all. Well, forget about the learning rate and about the regularization and all that. Maybe play around with the activation. You have rectified linear unit is the one that I told you about. It's 0, below 0, and then linear above that. And then you have the hyperbolic tangent, the sigmoid, and the linear. So these are the most popular ones. You can select different types of data to differentiate between, right? So in this case now, if I run this, this is what it comes up with, and even like a spiral thing. And then you will see how here is the struggling, right? So you see how it's trying, it's struggling. I don't know actually if we leave it run for a very long time, whether it will be able to come up with something. And you can actually, if you hover over these connections, so each of these, so these are, okay, let me explain everything step by step. So the first column here are the features. So this is what your inputs. So in this case, it's only x1 and x2, right? So the coordinates, the two coordinates, x1 and x2, x and y, really. Then you have two hidden layers. In this case, you can add or remove layers, and then you can add or remove neurons in each of these layers, okay? And in this case, your activation function is going to be always the same across all the layers and all the neurons. This, in practice, this doesn't necessarily have to be the case, okay? In this toy example, it has to. Yeah, you can play with the ratio of training and testing data if you want, adding noise, batch size. We haven't seen that yet, but the main thing is the number of hidden layers and the activation function, and maybe the different types of data, and see how it struggles really. So if I, as I said, if I hover on top of these connections, I will be able to see the weight. So the weight between the x1 and the first neuron is minus 1.6. Between x1 and the second neuron is minus 4, so on and so forth, okay? And this is also represented in how thick this line is. So this is a pretty cool toy to play around with neural networks. So you see in this case it's struggling. So we may think, okay, let's, I don't know, add more neurons here. Let's see what happens if we do that. Whether it's capable of learning or not. This is, I already know that this is, okay, no. I was going to say, I already know that this is not going to learn because of how these two lines look. But we will look at that later. Or actually, just in case, because I know that we are not going to have much time. So basically, these two lines, the black one is the test loss. So this is the how bad really is performing. So the lower the value, the better. This is how badly is performing on our test set of samples. And then the gray one is the training loss. So how badly is performing on our training set of samples, okay? So we want these two lines to be as close together as possible. So when these two lines start to diverge, so like here, for example, that the test loss started to go up. So that means that my model is overfitting. So that means that my model is fitting too well, excessively well to my training samples, and then is unable to generalize to samples that it hasn't seen before. Okay, so that's like if you only know 2 basketball players and then you are completely unable to identify or differentiate between any other basketball players simply because you don't know them by name. kind of like that. And then here is what happens if you use, so these are the other features, right? So what happens if we add x1 square, x2 square, or x1 times x2? So for this scenario, actually, we probably don't need that many neurons here, or even there, probably. Let's run this, see what happens. It's actually this. No. Okay, wait. Maybe I think for this one, we're going to need all of them. So this is just to show that sometimes the problem is not in the neurons or in how many layers you have. Let's add another one. But sometimes the solution is just to find if there is nothing better than having the right features. So for example, if you're trying to differentiate between people, there is nothing better to differentiate between people that having, well, actually, there will be nothing better, technically speaking, than having their DNA, right? But let's more practical, and in the context of healthcare, their NHS number. Okay, with their NHS number, you know that who is who. So you see, so now we are creating more complex things, but we still can't identify what happens if we add all the features. So there is a combination of these that will give you the right answer, which I don't remember. But anyway, this is a good example as well. Like, so each problem will be unique. So for one problem, it may be enough to have 2 hidden layers. For another one, you need 3 or 4. And the same with the number of neurons, okay? So the structure of your network will be very, very unique to your needs, really, to your problem.
Is there like a generalization, like that more layers or more neurons gives you something either faster results, and as you're talking about the features, that you need particular features to solve a particular pattern, is more better for all of these things here, or is it like an optimal thing that sometimes you don't get better results even if you've got like 1 million layers or something? Okay, so I don't know, have you guys heard about like how do you call it? It's polynomial regression. So this is just because this is the answer to that is very similar to the same question for the polynomial regression. So more is not necessarily better. So more layers, what more layers will give you are more complex boundaries, decision boundaries. Okay, but this doesn't necessarily mean better performance. This has to do again with overfitting. Not only with that, like in this context now of a neural network, more layers means that it will probably take longer to train, and training will be more complex. Again, because of what I said of what's going on with the learning algorithm when you have more layers. More neurons usually can give you also like more complex outputs, but basically more neurons, but more let me see how I explain this. So, okay, one way of thinking about this. So you see how I added different features here by clicking on them. Yep. So, and also, if you put that together with what we said before about the output of each neuron in layer 1, working as the input to the layer 2. Okay, so the output of layer 1 is the input of layer 2. Yes, that's what we said. So if you put those two things together, then
you can say that the output of layer 1 are the features used by layer 2. So by adding more neurons, you're adding more features. Okay, so if you look in this case, so you see how each neuron has like a drawing there. So this is the boundary. These are actually the features. This is the feature. So this neuron represents this feature. This neuron represents these features. It's just that it's a feature that is, again, is what we were saying before. It's a little bit hard to explain, but maybe not this one. This is like a cross. But it's something like this value, just x1, this is the feature that is representing. So below 0, above 0, right? X2, this is the feature that is representing below 0, above 0. If I have x2 squared, now you see that it's always blue except in the middle because the negative disappears because it's squared, right? So this is what the this is representing. If you go here, we have the same thing. So in this case, you see that this neuron is going to be 0 on this white area, and then it's going to be very, very positive on everywhere else, right? And this other feature is going to be like kind of this cross, right? So this is what this is telling. So when I add more, what I am doing is adding more features, which of course will change as I am training the network. So look, in this case, that was the solution. Actually, adding more features now on my layer 1. Yes. And this is interesting now because if you look at each feature, they are like circles with different radius, right? And then maybe some funny, but that's another actually interesting thing to explain. So you see, like this feature here, this neuron here, this is like a bit dodgy, right? Like you look at it and it's like, yeah, this is not really helping me my problem now. But that's fine. So this is the beauty of the neural networks. If you look at the weights that are applied to the output of this neuron when it goes to the inputs of the second hidden layer, the weights are very small, minus 0.13 and minus 0.12 compared to 1.3, I don't know, minus 1.1. So these are very, very, very small. So one ability of the neural networks is that they can say, oh, actually, this is not interesting. I'm going to multiply by a very small number. So it basically is the same as removing them. Okay. And in fact, if you are interested in this and you want to read more about this, there is a process called pruning in neural networks, which is similar to the pruning you do in trees, in classification trees. Okay.
But if you took that one out, you might not get the result. So even though it's a small negative weight.
Okay, so that's a very interesting question. Yeah. So if you take that one out without doing anything else, just taking that out, I don't know if we can do that here, can we? No. If you take that one out, then yes, it will affect the output. Now there are two things here, so yeah, one caveat of that and then one solution to it. So the caveat is yes, it will affect the output, but if this value is really small, if the weight is really small, how much will it affect the output? Very little, right? So that's the caveat of the answer, of the simple answer of yes, okay? There is a solution to that, which is when we drop a neuron altogether, then we may train the neural network a couple of steps more so that it can adapt to it not having that neuron anymore, okay, and counteract for this small variation that I may have introduced, okay? Yeah. Any questions? Any other questions? So the thing here is that,
sorry, those
yeah.
output test and loss, those lines beside it, what exactly do they do again? How exactly does that interpret?
Sorry, say again, I couldn't hear you.
Those lines by the output test loss and training loss, those lines there.
Yes.
How exactly do you interpret them?
Okay, so this is, let me see if I have this very early on my slides. So, okay, we can explain this now. So that is, so basically the way, just because I don't want to skip steps, but this is actually what we're going to talk about later. Okay, do you mind if I answer that question in a couple of slides?
Sure.
And if I don't, if I think I have and I haven't, please bring it back.
Okay, so you said something about converging and diverging.
Yes, I know. Sorry, I get excited and I want to tell you so many things. Okay, let's explain it. Yeah. So basically, the way you evaluate, so this actually is an equation. Okay. So basically, you have we were saying before, this is the equation for my perceptron. Okay. So if you think about it, you can now, with what I have told you so far, write the equation for this network, okay? Because this is basically putting a lot of this together, okay? So this is the equation for one perceptron. So basically, you know that the output of this is that equation there, right? And the output of this is that equation there, and the output of this is that equation there, blah, 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 blah. Of course, each of them with different weights, but that's what we're doing here, okay? And then what you will do is that now you have the same on the second layer, the inputs. So each of these AI values here, yeah, each of these A sub I values is a whole perceptron, okay? So if you expand this, well, yeah, so that's what I would like you to do, is to play around with it. Sorry, I was just reading the it said that it broke it properly by increasing the noise. So yeah, so you can expand. So basically what we have is an equation perfectly defined, and then what we want to do is we want to find the weights so that the values that we have at the output are the values that we need it to be based on the input, okay? So that means in our vertical and horizontal line things, we want the output to be 1 in certain cases, and we wanted the output to be -1 in all the other cases, right? So the loss basically is the difference between what I want to achieve and what I have at the output, right? So in practice, never say never, but you're never going to have exactly one when you want to have one, and you're never going to have exactly -1 when you want to have -1, right? So you're always going to, so what you are really looking at is something as close as 1 possible when you want it to be 1, and something as close as -1, for example, as possible when you want it to be -1. And that difference is your loss, okay? So that is how far, so in a way, the loss, I guess in a simple way of saying it, is how far you are from your objective. That's your loss. So that's why I said that the lower this value is, the better. Because the smaller that value is, the better, because it means that you are closer to what you really want to achieve. Does that answer the first question of what the loss is? I mean, that is the concept of the loss. Mathematically, there are many ways you can define the loss. So the square error will be 1, right? So what you have minus what you would like to have to the power of 2, and then square root of that, for example, square root error. So other name you have. Yeah, so that would be an example, but there are other types of errors that you can use, which I don't remember the names right now. So really bad with names.
Do you know in your diagram here with your orange dots, and each one of those has a weight? Which point do you apply? Where does the activation function represent on this? Is it times all of those for each layer? Do you just apply the activation function once to this? I couldn't quite work out how that fits into this diagram here on the screen, basically.
Okay, cool. Yeah, so you apply the activation diagram for each neuron, basically. So for each of these circles, or for each of these dots, you apply the activation diagram once, in a sense, once per each sample. So each sample has to go so you can't, so basically this is like you can run them in, again, the thing is that I know that you can't run them in parallel, but I know that in practice, when we code things, we run them in parallel because we apply like matrix or algebra, right? But matrix algebra. But the easiest way to think about it is that each sample is going through the network individually, and then you run the other one, and then you run the other one, and then you run the other one. So then every time you pass through a neuron, you have to run the activation function. Basically, every time you pass a sample, that sample is multiplied here for each of these weights. So each line will have its own weight, and then you will add up together inside each neuron, multiply and apply the activation function.
Yeah, I get you now. So basically down that orange line is you apply the activation function to the sum of those.
Yes, exactly.
And different layers will have possibly different activation functions, or they wouldn't be the same, would they? Or would they?
Yeah, you can have the same or different. So for example, I think I mean, I have played with different things, but then in the end, what I end up using is that they all have the same, except perhaps the last one. The output layer is a little bit special because you sometimes have, so for example, if you want to have this -1 or 1 at the output, you can apply something like the sign, because that's applying in like a hard threshold to your output. If you, oh my God, I'm really bad with names. If you have like multiple classes and you want to have something similar to a probability at the output, you apply something called, pretty sure it's softmax. Yeah, the softmax function. Okay, which it basically it kind of well, without the kind of, it normalizes all the, so if each of these neurons, which is usually what you have, so if each of these neurons in their output layer correspond to a class that you're trying to identify, then it normalizes whatever output you have here, also called the score. Okay, just so that you know, if you find it in the literature or around, it normalizes so that the sum of all of them is 1. In short, that's what it does. Okay, and then you can interpret it as a probability. It's not really a probability, but you know what I mean. So it helps with the interpretation of the output of the, artificial neural network. Just again, this is an example of why I want to give you the basics, and then you can, there is lots of things that you can learn. So if I type, what did I type? Neural network loss functions. So literally the first result is a block with it teaches you about these loss functions, or neural learning as optimization. What is the loss function? So it tells you what it is, and then it tells you the maximum likelihood, the cross entropy, and in this case, it only tells you that. But you can find, as I said, there are many different loss functions. Okay, it tells you a little bit about them, and then you can read about them, and probably will give you the equation. In this case, it even gives you how it can be implemented in whatever this is, what it is. This is Python. Okay. But again, the key idea is that what the loss function is, which is it's just how far you are from your objective, really. And then what I said about we don't want this to be converging is because you will be overfitting or overtraining your model, and you don't want that to happen. Okay, that's a very common, I guess, error in when people are starting to use machine learning in general. So they look at the training error. It keeps going out.
Lines are together.
Sorry, second.
So the way they are now, that means it's overfitting, right?
So the way it's here now, it doesn't look like it's overfitting. So when it's overfitting, you can see this line going up, still going up. Even though on the train, so you can see the testing line, so the black line going up, and the training line, the gray line, goes down. So it's telling you that your loss for your training samples is getting smaller and smaller and smaller. It's like I'm getting so good at differentiating my training samples, and it's getting so good. But your loss for your testing samples is getting bigger and bigger and bigger, which means that you're actually getting worse at generalizing your model. Yes, so you are getting better. You're getting expert. It's kind of like you are getting expertise on differentiating the samples that you know, that you have, that you can see, that you have used for training. That's your knowledge, right? But all of this is useless unless you can generalize your knowledge to the outside world, meaning samples that you haven't seen during training, right? So that's why you want to be good, not on your training, but on your testing. So in a very, very funny scenario, you may find that sometimes coincidentally, you can have a training loss that is higher than your testing loss, right? So you are actually worse with your training samples than you are with your you are worse with your training than when you are with your testing. Happy days.
So the way those lines are right now,
yeah,
that's good.
That's good because it's going down for both. If we
going down for both.
Yeah. So
okay, but if it was a single line itself, like okay, that they are joined to one single line, or you can barely tell the difference, would that be bad?
If you could barely tell the difference, that would be good as well, because that means that what you're seeing in training is exactly what you're seeing in testing. So actually that would be brilliant, because that it's telling you, look, I can train my model and I can know with super high certainty how my model is going to perform in the outside world. That is a problem of all machine learning, really, which is, okay, you build a model, you build an application, whatever, in the context, for example, of healthcare, you build an application to differentiate between malignant and benign cancers, but you build it with some data that you have. And then you give that to a clinician. And the problem is that, or the problem occurs that, or there is a risk there because you don't know exactly how your model is going to perform when the clinician uses it. Because there is no way to know. But if you have if your training sample is representative of what you can, of all the variations you can see in the world, then you have a higher chance that what you see in training is what you're going to see in testing. And then you are confident that you are more confident of how your model is going to perform in the outer world. Okay, so I'm going to give you now, not in the context of healthcare, but maybe you have heard about this. So, so Tesla, have you heard about Tesla and their autopilot? So they were saying they gave a talk, I guess, a while back about their autopilot capabilities and how they have been able to, how they are ahead of the game simply because they have been recording data from their cars that the customers use, and they have been using that data to train their models, right? And then there was something very, very interesting, which is they started to talk about corner cases, which are cases that you have never, ever, ever seen. And then when you find one of those cases, who knows what the model is going to find to decide. So in that context, they were showing pictures of, I don't know, cars pulling from boats, maybe, or maybe when you are carrying your bike on the back of your car. What is that? Is that a bike crossing the road? What is that? So those are things that, that you don't expect to see, or they are not that common. So in the healthcare scenario, you may have cases of cancer that are different to what most of the other cases are. So they may be a little bit, you can think about them as outliers if you want, but sometimes they are not as much, they are not that far away as an outlier. It's just that maybe they are not that common, let's say, okay? Your model, especially in this context of healthcare, your model needs to be able to deal with them in a way that is not risky or harmful. Yes, does that answer the question? So this is a clear example of diverging. So you see how now the gray line keeps going down very quickly, and the black line, it's not moving, or if anything, it's even going up. You see how they are going far, far apart, far apart. It's getting worse and getting better at training. The training loss is going down, but my testing loss is going up. And now it has plateau there. Yeah, it may be the case. Sometimes it goes up before going down a little bit, before going down a lot. Okay, but it's something that you need to watch for. So in this case, what happened is that I am giving it very few training samples. So then it's not able to identify that the pattern that I'm trying to classify here is a spiral. So then the network just can't do its thing because it doesn't have enough data. And you will find the same in whatever application you use. The data you have for training is crucial. Questions? Okay, so yeah, so this is what we're saying. What is the learning algorithm? So we're going to talk about the steepest gradient descent. And I kind of made up a game for this. I don't know how this is going to work through Zoom, but let's see what happens. So this is the game. So you are, you live in the bottom of a valley, okay? But now you went out for a walk. So you are out and about at a higher position now, of course. And it's super, so you have a horrible fog. You can only see, 1 meter away from you, okay? So basically the only thing that you can tell is, so let's say now in a 2-dimensional world, okay? You can only move left or right. Yep, so so this is what I'm trying to explain. So you live here. This is your house. Nice and cozy. But you are out and about. You're maybe here. Okay. Super horrible day. You have had enough. You want to go back home. Let's say you can only move left or right here, but you don't see your house. You don't see anything really. You only see 1 meter away from you. So 1 meter to the left and 1 meter to the right. The only thing that you can tell by that is whether you're going up if you go to the left or down, or whether you're going up or down if you're going to the right. Yes. So let's say that I tell you that the ground on the left is higher than the ground on the right. Will you take a step left or will you take a step right?
Go to the lower ground, is it?
Yeah. So you take a step right because you know that you want to go downhill. So then now you take a step and then you check again. And then you check, oh, am I, and then you see that your left is higher than the right. So you take another step right. You continue doing this until you reach home. Yes? Is that clear to everyone? Is that obvious to everyone? Because I want it to be so clear that it's obvious.
Please, can you repeat that again?
Yeah, okay. So imagine, so from the top, okay? Imagine that imagine you are on the top of a hill, okay? And you want to go to the bottom of the hill, yes? And you can only take 1 step left or 1 step right. And you can't see anything. All you can say, all you know is whether the ground on the left is higher than the ground on the right. So that means if the ground on the left is higher than the ground on the right, then that means that to the left is going uphill and to the right is going downhill. And if it's the other way around, then it's the other way around, right? So if the right is higher than the left, then going right is going uphill and going down is going downhill. Now, that's all you know. Is left higher than right or right higher than left? So now you need to decide, do I go left or do I go right? And you want to reach the bottom of the hill. Okay, that's your objective. You want to go all the way to the bottom of the hill. So if your left is higher than your right, what did you go, left or right?
Funny, I'd rather go right.
Yes. So you will go right because you want to go downhill. And if your left ground, the ground on your left is higher than at the ground on your right, then going left is going uphill, going right is going downhill, so you want to go to the right. Yes?
Okay. Yes, but what do you mean by one is uphill? I thought I was at the top of the hill.
Yeah, so you were on top of the hill, but you want to reach the bottom of the hill.
Okay. So, but why should one side be going uphill and one side going downhill if I'm at the top of the hill?
Sorry, say again?
Why should one side be going uphill or one side be going downhill if they should be both going downhill if I'm at the top?
Ah, okay, see what you mean. Yes. That's a very clever question, because actually that's a problem of steepest gradient descent. So sometimes, what if left and right are at the same level? What do you do now? You don't know whether to go left or to go right. So that's one of the problems that the steepest gradient descent algorithm will find. It could also be the other way around. You can find a minimum where, so it could either be because you are on the top of a hill or because you are on the bottom of the hill. I guess if you are at the bottom of the hill, it's not such a big deal because you're already at the bottom. That's where you want to be, right? But also you have to think, well, we'll get there in a minute as well. But yes, you are absolutely correct. If you're at the top, then you kind of don't know what to do. Okay, but let's forget about that case for now. Imagine that there is no top. So then, do you understand how the principle of going downhill works when you only know whether the left is higher than the right or vice versa? Yes?
Yep.
Cool, perfect. Because that's all we do. That's the steepest gradient descent, and that's what we do. This valley that I have drawn here, this is my loss function. This is my loss value. Okay, my y-axis is the value of my loss, and my x-axis is the value of my weight. So let's say that I am just trying to optimize a perceptron with one weight. Okay, so this is whatever value. Let's say that for example, let's say that the best value for my weight is 1. Okay, so if I move away from 1, then my loss goes up on either side. Yeah. So basically what I'm saying here, when I say that this is my loss function, what I'm saying is that if I were to try all possible values for my weight, this is what I will draw. This is the loss that I will get. Do you see that? It could also be an equation. Let's say that the loss is my output minus 1. And my output is my input times my weight. Then you can draw what your loss is based on your weight. So, right? So f of x equals y. So this is what we're doing here, really. I know that this is a little bit more abstract. Please do ask if it's partially clear, what is not. Nothing is clear.
Partially.
Okay, so let's say that my loss equals 1 minus my weight. This is an example, okay? Very simple example. If this is my loss, now I can draw my loss. Actually, let's say that is 1 minus to the power of 2, okay? If this is my loss, then I can draw this line. I can draw the loss, the line of the loss based on my weight, against my weight. So if I go, so we have just said that my loss y equals 1 minus x, which is w, to the power 2, right? So you see, this is what I'm drawing here. This is just a like an app in the web browser that is useful. So this is what I have drawn here. Okay. Now this is my loss function. My loss function could be something else, or it could be more complicated. I could have here, I don't know. Does that work? Sine. Yeah. Sine of x. Oops. Yeah. So you see, in this case, the loss is quite ugly. Now you have there's a sigmoid. Do I have the sigmoid here? Nope. Okay, so they don't have the sigmoid. But anyway, what I mean is that because I know what the equation is mathematically, then I can plot it. And it just happens in this scenario that we are discussing now that this is the loss. It's something like this. It looks like a bowl. Yep. So what I'm saying when I say that this is my loss function is that for each value of x, for each value of my weight, x, w, whatever letter you want to give it, for each value, I have another value for my loss, and I know it looking at this graph. Yes? Please do say so if it's still not clear. Please, please, please.
It's not clear.
Okay, perfect. Okay, let's go with step by step then. Is it clear what the loss is? It's how far we are. We said that is how far we are from my objective. Is that part good or bad?
Okay, that's understandable.
Cool. Now let's say that my
Good.
okay, so let's say that fine. So now when I say that this is my loss function, it's actually just a graphical representation of that. So what I'm saying is I know how far I am from my objective for every possible value of my weights. So let me rephrase that and let me break that into parts. So we know that the output of my network depends on the value of my weights. Yes? Is that clear? That concept clear, I mean? So when we were looking at the vertical line, horizontal line, then the output that we were getting was dependent on the weights that we were using. Yep. Yes? Okay.
Yes.
Okay, cool. So that means that I know that, of course, my output, we said my output is going to change based on the weights that I'm going to use. And now if I take that output, I'm saying that my loss is how far this output is from my objective. Yes? So if we put those two pieces together, this means that my loss is going to depend on my weights, right? So my loss depend on my output depends on my weight, meaning my loss depends on my weights. Yes?
Yes.
Cool. Cool. So then this graph here is just a graphical way of representing that relationship. Okay? So what that is doing is I'm really plotting the loss value for every value of my weight. So I'm checking what happened to the loss when the weight has a value of 0. This is the loss. What happened to the loss when the weight has a value of 0.1? This is the loss. What happened with the value 0.2? This is the loss. Blah, 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 blah. All that until I cover whatever ground I want. And then I basically plot all those points in here, in a graph. Yeah. So when I said, let's break that again into 2 steps. So what is the output when my weight is 0? Like we were doing before. If these are the weights, what is the output I have? This is the output. Okay. How far is that output from my objective? This part. So that is my loss. Okay. That's what I have done here. So now I try another weight, a little bit higher, maybe I move from 0 to 0.1, get the output to loss. 0.2, get the output to loss. 0.3, get the output to loss. Yes? And at the end, at the very end, what I'm doing here is plotting those 2 values. So that graph. So I have in the x-axis, I have my weight, 0, 0.1, 0.2, 0.3. And on my y-axis, I have the loss for each of those points. Yes?
Yes.
Cool. So then that's what I was trying to convey. So that is what we call the loss function. Okay? It's how the loss changes when the weight changes. Yes? Is it
Yes.
clear now? Cool. Cool. So if I can see this line, then I can go straight to the minimum here. And then so if I'm given this graph, I will go look for the minimum, check the x-axis and say that's the value I need to give to my weight, solve the problem. Yep. Okay. So so now again, this is another way of putting it. Okay. So you have a ball and you put you have a bowl and you put a ball into the bowl or a marble, and then you let it roll, and it will move, it will roll all the way down until it stops at the bottom, right? That's what Steepest Gradient Descent does. So copy link. This is an example. So you see how it's going down, and then at the end it stops there. Yep. It's just an example, okay? Don't get too. And then I'm going to give you another example of when things go wrong. So you see how now it's unstable. Okay. So why do you have any suggestions of why this is unstable? What is the ball doing? Or what is the dot doing?
Since it's moving in both directions.
Going both directions. Yeah. So it's overshooting really the minimum, right? So it's always going too far to the right, then it's trying to correct, but it's going too far to the left, too far to the right, too far to the left, blah 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 blah, and it stays there. Yep. So that's what we manage with the learning rate. Okay. So how far your step to the left or your step to the right is dependent on the learning rate. So it's basically directly dependent to the learning rate. So the learning rate is kind of without the kind. It's a number that you multiply your step by. So if I multiply if the learning rate is 1, then I'm taking 1 step. If my learning rate is 3, I'm taking 3 steps each time I take a step, if you know what I mean. Each time I decide to go left or right, I will be taking 3 steps instead of 1. Yes? And then I can get into this cycle of overshooting my destination all the time in my system. Okay, cool.
I think it's because Pete left the room, and whenever Pete leaves the room, weird stuff happens on Zoom. So sorry.
Yeah, that's all right. That's all right. Any questions about this? So far, so good? Cool. So then, now let's play a little bit with the steepest gradient descent. Now let's try that you're really in a hurry. You need to go home. You need to get home, whatever reason. You need to go to a loo. You need to get to home quickly. Okay? Now, you need to think of ways to get to home quicker, faster, on the same, with the same limitations that you had before, in terms of you only know whether the ground to the left is higher than the ground to the right or vice versa. Okay? So how can you do that? So one way, for example, we have established already that is, okay, instead of taking 1 step, I can take 2, 3, 4 steps. Okay? But another way will be if I tell you that going down is on the so to go down to the left. If I tell you that the right is downhill, so you take 1 step to the right, and I tell you again, yeah, right downhill, another step, right downhill, right downhill, right downhill, right downhill. After 100 times, you're just running, right? You're not waiting, you're just literally running to the right. And that's a way of saying that you're picking up your pace. You become more confident that, okay, this is definitely the right way. Yeah, this, sure, right way, I'm going, yes, yes, yes. So that is momentum. That is the steepest gradient descent with momentum. And that exists. That's something that we do. Okay? So that's only a way of showing you, how these things, they can be intuitive, right? And then, of course, you tell me, yeah, but then, Marcus, what happened? You start running too fast. That means you're taking your step is too large. Then you're overshoot the minimum. Say yes, but it's exactly what happens when you let a ball roll in a bowl, right? So it accelerates, overshoots the minimum, then it stops, go back to the minimum, overshoots, and every time it overshoots the minimum by less. And at the end, it becomes stable in the minimum, it stops there at the bottom. Yep. So that's just an example. There are many other ways that they have modified the steepest gradient descent to make the learning faster and faster and faster. Okay, and we'll see examples later. And now to go back to this thing about what happened when you're on the top. So now this is what I have told you is like the ideal world. That, that theory, it never happens. Your loss function looks more like this. It's like a roller coaster. Okay? And then you have traps if you want. You have what's called local minimum. So you start going down, 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 and then you know that this is going up, this is going up. Oh, fine, I'm at the minimum, solve my problem. But not really, because your global minimum, which is the point that you really want to reach, is here. So those are things that we need to deal with, okay? And so of course here it's very clear that you are on a local minimum because we can see the whole graph. We can see the whole loss function, the whole loss graph. But in reality, we don't know how this graph looks like. We know that it's going to be messy, but we don't really know how it looks like because calculating how it looks like, it will be super, super computationally expensive. And it will defeat the whole purpose of artificial neural networks because that will be equivalent to trying every possible combination of weights, which, as you can imagine, is not possible. And then also, it's going to be, if we want to identify the minimum point by eye manually, then it's also going to be very hard because in this scenario, this is how we will represent the loss when we only have one weight. But that's never going to be the case. You are going to have, if you have two weights, you are going to have a 3D graph here. If you have three weights, you will have to plot a 4-dimensional graph. And then if you have 4 weights, I don't know how you're going to do it, probably adding, it will have to be a video or something. And then higher than that, no idea. And usually your model has hundreds of weights. So it's not really something that we can eyeball in terms of where the global minimum is. So where I am trying to get to is that when you reach a local minimum, you don't know it's a local minimum. So that's a problem. Yep. Any questions so far? No? Okay. And this is where we are going to look at different learning strategies. So SGD is stochastic gradient descent. So this is just a gradient descent that we looked before. Then we have the red line is what happens when we have momentum. Can I zoom in for you to see? Yes. I hope you see that better now. So you see how with momentum is going faster than the normal gradient descent. And then you have other types of learning. They are just basically different modifications of the basic gradient descent, okay, that I'm not going to get into now. But you can look it up. It's just a small, each of these are kind of like incremental modifications of the gradient descent. Like, for example, the momentum is just adding a momentum term, saying, well, if you're going that way, keep going that way, corrected by whatever you're seeing now. Yep. There are other examples here. No, wait. This is another example with another surface. And this was just to show. So for example, this is an interesting one because it's showing exactly what one of you asked, which is what happens if you're at the top and you don't know whether to go left or right. So if you look at the red point here, it's kind of stuck there. That is because the gradient, so it's able to tell which way is up or down in this direction, this axis, but in this other axis, which is at the top, it can't, so it doesn't know whether to go to the left or to the right. Yes? And it actually doesn't have to be that it's the slope on the left and the slope on the right are identical. It doesn't have to be identical, not the slope. If you want, it doesn't have to be that the height of the ground to your left is identical to the height of your ground to the right. It doesn't have to be like that. If the difference between the two are is very, 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 very small, then the gradient descent won't work properly, because then the difference is so small that the confidence that it has on going left or right is very small. So the step that it will take is very small. Yes, because the size of the step is based on how steep the slope is, the slope that it can see is. Yeah, so for example, if we go here, the step that it will take here is larger than the step that it will take here. And then again, this is another one. No, this doesn't work apparently. Okay, and this is just an example that you can look it up and look at the equation and look at, this is actually this third link that I'm giving you in the slides. It's a super nice, at least I like it, a blog about learning algorithms. And it explains all these learning algorithms very nicely, I think. And it explains them as what they are, which is incremental changes to the basic stochastic gradient descent, right? So it starts with momentum. It tells you the difference between the momentum, and it shows that the momentum is just this term here, right? So it's just adding a momentum to the velocity of how you're moving. And then it tells you about this Nesterov accelerated gradient, which is another way of calculating how you're moving. I'm not going to look into that now, but we don't have time really. And then, ADA gradient and all that. And these are, again, all of these, they were super popular, and at the time, they still are. And at the time when they came out, they were at the front of. They were winning competitions, for example, in terms of how fast they can learn. And they were part of the reason why artificial neural networks are so popular now as well. Which is, okay, now it's not just that we have more computational power, but also that we know how to train the models faster, so we need less computational power to train the models. Yep. So just to wrap this up, and then we can have questions, pros and cons. Pros, the model can fit very complex data. So again, this is similar to what happened with the nearest distance-based classifier. It's entirely data-driven, which means that you don't need to tell it anything about the data. You just pass the data and it will do its thing. There is a good thing about this compared to, for example, distance-based classifiers, which is, as we said before, it's capable of saying, nah, this feature is not interesting. I'm going to ignore it. And then the cons is that it's a black box method. It's not a black box method in the sense that we don't know really what's going on, but it's just hard to explain. That's why I don't like the term black box, because black box kind of implies that we don't really know what's going on. We know, but it's just hard to convey in a way that is understandable for us, in a simple way. It can be slow and computationally expensive, and sometimes even memory hungry as well, if you are trying to create a huge network. But this is only for training. So it's the opposite than what we saw with the distance-based classifiers. Distance-based classifiers were very fast during training and slow during testing. Artificial neural networks are the opposite. They are slow during training, but super fast during testing. This is what we really want, usually anyway. And then the other problem is that they may need a lot of data. So they are very, very data hungry, which is another reason why they only became popular recently, which is until now, we didn't have the amount of data that we have now. As you probably know now, nowadays, data is a very, expensive commodity to have. Any questions? You probably have a ton of questions, so do ask, please. No?
I think what we'll do, Marcos, then is we'll take a 15-minute break, and then if you could just, within sort of half an hour, demo the R code. So you've given 2 examples. That'd be great. Okay.
Yeah. So see you all at 4:07 if you want.
Say 4:15.
Okay, fine. 4:15.
Yeah. Cool. Okay, brilliant.
Thank you, Aaron. We have 15 minutes to fly through the code of artificial neural network, and I guess, yeah, well, and then to answer questions that you may have. So, as we go through this, I'm actually going to be explaining things that I haven't explained before because it's necessary and it has to do with maths, but I will do that very quickly. So as before, we read the data, we split the data into training and testing, blah, 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 blah. That's completely agnostic of the model that we're going to use. And from here on is when we start defining our artificial neural network. So the first thing I'm going to do is to define what my activation function is going to be, and I'm going to use in this example the sigmoid, right? So I create a function called sigmoid that just calculates the sigmoid of a value x, okay? And now I'm going to create a function that gives me the derivative of the sigmoid, okay? Why am I doing this? Because that's the mathematical way of knowing whether left is uphills or downhills, or right is uphills or downhill. So if you remember from algebra in school, the derivative of the function tells you the slope of that function at a given point, right? So it's basically the tangent line to a curve, right? So that's the derivative. It's not the line, it's the slope of that line. But yeah. So that is what I'm going to use to know whether I should move left or right. Okay. So that's something new that we didn't specify before. We said that we were moving left or right, but we never knew, okay, but how do you know that left is uphill or downhill? And this is how, okay? Mathematically, using the derivative of your activation function. This will already tell you that there is a criteria for an activation function, and that criteria is that it has to have a derivative. Not all equations have derivatives, and not all equations have derivatives defined across all the values, x values. So, for example, if we look at the step function, this one here, at 0, it doesn't have a derivative there. So then you say, okay, Marcus, you just said that it has to have a derivative, and now you're saying that there are activation functions that I hardly use that don't have derivative defined on all its values. Yes. So it's not, so it has to have a derivative in the great majority of the values, let's say that, okay? So it's not a super strong criteria. If it doesn't have a derivative in a specific point or 2 points, then there are works around that, okay? There are ways to work around that. Okay, so we have now the activation function all sorted and its derivative as well. Cool. Now we define the neural network, and in this case, this neural network is going to have one hidden layer and the output layer. And the output layer is fixed to only one neuron, okay? Because this is going to differentiate between positive and negative classes, benign and malignant. So I only need one neuron, okay? You could also have 2 neurons, 1 per class. In this case, I'm doing it only with 1. Positive or negative, that solves it. Yep. So this is my function. As input arguments, I have the learn. This is only to define, to initialize the network, okay? I have the learning rate, number of factors or features, if you want, and number of neurons in the hidden layer, okay? These are the parameters for my network. And then, yeah, all I do, because I'm only initializing, I'm not training, all I do is just save the values, right, in this model structure. So, sorry. So let's go here first. I have my learning rate, and then I have my parameters, which are the weights. So I have a weight matrix. So I say, so we work with matrix in neural networks, and you will see why later. And this is what we were saying before. So then so the number of weights that I'm creating is the number of factors plus 1. This plus 1 is a bias term, okay? And then I initialize these weights with random values, okay? And in this case, this is again what we were saying before. This randomization, it's a little bit special, a little bit controlled. It's random, but it's from a normal distribution, okay, with 0 mean and unit standard deviation in this case, okay? There are other ways of initializing the weight. And I create another weight matrix for my output layer, okay? So each layer in an artificial neural network will have its own weight matrix, yes? And in the matrix, the way you can think about the matrix is that each row corresponds to a feature, yes, in this matrix, and then each column corresponds to the one neuron in that layer, okay? That's how we create. It will be flipped around, but you will see now why it's interesting for us to define it that way. Yes, so far I have just initialized the network. Now, train the network. This is the interesting part. So the training of a network happens in 2 steps. The forward pass, and the backward pass. In the forward pass is when we move the inputs through the network. So we multiply the inputs by the weights, and then we add up together all the inputs for a neuron, apply the activation function, and then we move to the next layer and the next layer until we get to the output, right? That's the forward pass. Yes, so we move forward in the network. Then is the backward pass. In the backward pass, what we're doing is, based on the output that we had in the forward pass, we calculate our loss, which is how far is that output from our target. Yep, from our desired output. Okay. And now we move that loss, that error value, backward in the network. And when we run it backward, instead of using the activation function, we use the derivative. Okay, and what that is telling us is the derivative. The other thing that the derivative tells us is of a function. Okay, I'm not talking about networks. This is maths. If I have an equation, let's say y equals a plus 2 times b. Okay, a. Let me type this down so that you guys can see what I'm talking. Y equals a plus 2 times b. Okay, this is the equation that I'm talking about. Now, the derivative of y with respect to a, partial derivative now. Okay, so this is a variable and this is another variable. This is telling me how y changes dependent on a, sorry. So this is what I was telling before. So what happens when I change my weight? How does changing this weight affect my loss? Okay, so that is what the derivative is telling us. Yes, so this is just, again, I need to tell you, it's maths, but I need to tell you so that you understand how is this training happening. And then the derivative with respect to b is telling us, okay, how is y changing based on b? Okay, what happens to y when b changes? Okay, and now a and b, if you think about it, a and b is like this example that we were, or this game that we were playing about moving left or right. It's a value. You can either go larger or go smaller. You can't move in any other direction. So you either make it larger or make it smaller. Yes? Cool. So yeah, so what we are back propagating again is not the output per se, is the loss. Okay, so then what the derivative is telling us is how the loss is changing based on a weight, right? And then now we can adapt all of the weights to make the loss go smaller, 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 right? So that's the plan anyway. So for the training, we need our model, which is what we defined previously. And then we have the training data, the training labels, and then how many times we're going to go through the learning process, okay? Number of iterations. And now there is something here that I didn't really explain there up here, which is normalization. So I said before that it's super important in artificial neural networks that all the input factors or features or whatever you want to call it, it's very important that they behave, that they have similar ranges or the same range, okay? So usually what we do is zero mean and unit standard deviation. Yes? So this is similar again to what we, yes?
Sorry, Marcus, do you mean, is that like same thing as scaling?
Yes, exactly. So we are scaling, yeah, exactly that. We are scaling the input factors so that they all have something like zero mean and unit standard deviation. Okay, that's what we are doing. Okay, and now this is something very important, which is notice how I define. So for that, if you remember set normalization, if you remember, you basically divide by the mean, subtract the mean and divide the standard deviation. Yep. So the value minus the mean divided by the standard deviation. That's how we do this scaling. Yes. Set normalizing. Now, of course, you need to know what that mean is and what the standard deviation is, because those are two constants there in that function. So, and then now this is very important. You calculate that mean, that standard deviation, only using your training data. Only using your training data. So, rule for all machine learning. If you need to modify, if there is a fact, if there is a variable in your model that depends on data, that data can only be the training data. Okay, I'm going to need a couple more minutes to finish this, but I tried to go as fast as possible. Just give me a second. Lara, nos puedes por mí si no quieres, ¿vale? Pero pues se puede alargar. Entonces, si quieres ir y volver a... Vale, yo te llamo después. So that's very important, okay? And that's a rule to apply across all machine learning, really, because otherwise you will be cheating, really, okay? Because you will be using data that is used for testing to set parameters in your model. That's not how you're supposed to do it, okay? Fine. So this is what I do here in the training. First step is I calculate the mean and the standard deviation, and then just apply the normalization, okay? Fine, then I prepare some constants, blah, blah, blah. This is just me preparing some variables here. Same for the loss. I create a vector because I want to keep track of the loss at each iteration. This is just me wanting to do that in order to plot at the end so that you guys can see how the loss goes down. And now is when we go through all the iterations. So you see I have, for each iteration, we have the forward pass and we have the backward pass, okay? In the forward pass, we go layer by layer. So first, hidden layer 1. We only have one. If we had multiple hidden layers, we'll go hidden layer 1 first, hidden layer 2, hidden layer 3, etc. Okay? So what do we do? So look, this is the trick I was telling you about. So I'm going to add, this is what this is doing. I'm going to add a value at the end of each sample, and that value is going to be 1. I'm appending a 1, and this is what we're going to use for the bias term, okay? Because our weight vector is 1, it has 1 extra weight, that is the bias term, okay? This is just a trick, fine. You could have done this separately as we saw in the equation, but it's just easy. I think anyway, it's just easier to do it this way. Now, second step, we multiply each feature by its weight, yes? And then we have to add up together all those values for each neuron, yep? So that all the inputs multiply, and at the end, they add up together, and we have a value. That's for this neuron. And then we have the same for another neuron and for another neuron. Yes? Cool. So how do we do this? Well, this is the matrix multiplication. So just very quickly, very quickly, you can do this by just multiplying two matrices if they have the right shape. So if you remember, multiplying two matrices was rows times columns, and then you're pretty much you do is so 1 1 multiplied by 1 1, 1 2 multiplied by 2 1, 1 3 multiplied by 3 1, and then you add up together all those values, which is what we're trying to do. This is also why we use matrices, right? Instead of individual vectors, where you have a matrix, And this is why we do the matrix so that each column is one neuron and each row is one feature. Okay, this is just a trick. Fun fact, this is also why you may have heard that GPUs, graphic processing units, graphic cards from computers are very useful for AI, artificial neural networks. Okay, because they are really good at doing matrix operations. Okay, anyway, now we have the input for each neuron. It is usually represented by Z. Now we just applied the activation function, sigmoid. Happy days. Now we have the output for the hidden layer. And now we repeat exactly the same for the output layer. So note how this is doing exactly the same for each layer. Okay, so now we do the same for the next layer, for the next layer, for the next layer, until we have run through the whole process. So exactly the same thing. And at the end, I have the output of my new network. Yep. Good. We have finished the forward pass. Backward pass. We now, first thing we need for the backward pass is the loss, the error. Okay. In this case, I use the mean square errors. There are others, as I said here. But see how Y, this is the input parameter. I said I had X, which is the data, Y, which is the labels or my goal, right? So this is what I want to have. That's my objective. So look how I simply do Y, which is what I want to have, minus what I got from the network, square, and then calculate the mean across all the samples. Yep, across all the samples. Yes, so that's why it's called mean square error. So it's the mean across all the samples, all the training data. So that is why. So now I have the loss of my network at this point. Okay, this is how far I am as the mean in average, how far I am from my objective. Fine. And now I move that backwards. So that means first I go through the output layer, then I go through hidden layer. Let's say there are 3, hidden layer 3, hidden layer 2, hidden layer 1, and that's it. Yep. And then what we do is basically, if we were to write this on a piece of paper, then we will do the derivative of all these equations, and that's what we're going to do here. So you see here, I say we need the derivative for each point, for each point in the network. So look at where we start. We start with the error itself. So this is the error. So look, this is the derivative, if you remember, right? So the derivative of x to the power of 2 is 2 times x, okay? So if I'm doing the derivative, this is the derivative of the error with respect to the output of the network. Then I calculate the derivative of the output with respect to the input of each of the output neuron, in this case, because there is only one neuron. If I were in a hidden layer with multiple neurons, I would move backward, and I will calculate the derivative with respect to each neuron, right? So this is, as I said, imagine that we are actually going forward, but now the activation function is actually the derivative instead of the activation function, okay? But we move in we do the same thing, basically. We go backwards, literally line by line in the graph, okay? Yeah, so basically that's what we do. Yeah, I'm not going to go through all of this into detail, but this is what we're doing. This is the derivative. If you want to do the maths, you can check the maths and make sure that I haven't made any mistakes. It's working, so hopefully there aren't any mistakes. And then, as I said, then we move things backwards Now that I know what the derivative between each point is, I can move the signal. I can move the error back propagate the error in the network. And what I have, these are the interesting terms. Derivative of the error with, this is what this means, is derivative of the error with respect with the weights of the output layer. This is saying how the error changes relative to the weights of the output layer. That's what I want to use. And then I have, this is another one, which is interesting for me, which is the derivative of the error with respect to the weight of the hidden layer. Again, this is the other interesting one, because those are the parameters that we are going to shift. Those are the ones that we are going to tune so that the error goes down, okay? So that we are going to go downhill. Once I have these two parameters, I update the weights in the direction of the derivatives, means downhill, okay? So okay, so I calculate the mean error. So this is why I'm dividing it by the number of samples. That's what I'm doing here. Forget about that for a second. I have derivative of the error with respect to the output weights. Look what I'm doing. I multiply that derivative with the learning rate. Remember the learning rate? We talk about it. And I said, it literally tells you how big your step is because it's literally multiplying. It's a multiplicative factor directly. And this is exactly what we're doing. We multiply the learning rate with the derivative, okay? And then we are saying that my new weights are equal to my old weights minus the derivative of the error with respect to the weights times the learning rate. So it's this thing here that I'm highlighting, the derivative and the learning rate. That is my correction factor. That is telling me how I need to change the weights, okay? Do they need to go left or right? This is the key point here. And all I do is my new value is my old value corrected, okay? Mass, plus, minus, and a value. And I do the same with the hidden layer. Done. Okay? Now the key here is that I do over and over and over and over and over again. Okay? So in theory, if we were to set the learning rate to 1, okay, this will be like solving the whole thing into one step. Okay? But because we have so many parameters, we set the learning rate to a smaller value, usually 0.001, 0.01, 0.1 sometimes, and then values around that range, okay? And then instead of trying to solve the whole problem in one step, we're taking little steps, okay? Little steps, little steps, little steps, getting closer and closer and closer. And this is because that way we allow, you know, when you change a value of one weight, then it may be that this other weight that before had to move that direction. Now, because you have changed the other weight, now it has to move the other direction, something like that, okay? So it kind of allows to, allows to correct for dependencies across weights, okay? Something like that. Cool, that's all. And then, so you see how many code we were saying? Training an artificial neural network takes time. Now, what about testing? Testing, super fast. So what we do, we normalize, we apply the mean and the standard deviation that we calculated during training, okay? You see how I'm only applying, I'm not calculating anything. And then we run the forward pass in the same way we did before during training, but only the forward pass. And it's exactly the same code. We move forward in the network. That's all we need. That's it. That's our output. Okay. So let's see if this works. So first, initialize the model, nothing happens really because I'm just initializing. And this is for you to see the shape of the matrices. If we have time, we will talk about them because it kind of tells you a little bit of the story as well, but we are running through everything. This is, so I have run this with 5,000 iterations. I have trained my network for basically 5,000 times. I have gone through the training data 5,000 times. I have taken 5,000 steps, okay? And this is the error. So you see how the error goes nicely down. Yep. And now I just test new data. We apply a threshold. This is what I was saying before. My network is giving me a value between 0 and 1, okay? Because that's what the sigmoid does. But I need it to be 0 or 1. So I just apply a threshold 0.5, okay? I plot the error rate, 95 point, sorry, the accuracy, 95.9%, 96% of accuracy, okay? If I were to change, I could change if I want here, number of hidden networks, neurons, sorry, 10. This will take longer to train. Yep. And now I test it. Success rate 95.6. It's actually worse. And if we see this, we don't see any difference, but there is a key thing here, which is that the error, the loss, the error keeps going down. So this is telling me that maybe if I keep training, I will get better, okay? If instead of 5,000 iterations, I go through the data maybe 10,000 times, maybe my accuracy will go up, okay? But then at the same time, I'm only showing here the training loss, not the testing loss. So then here, I'm not showing what's happening with the testing loss. If it's going up, then I'm overfitting. So those are the things that you guys need to be careful with. I was going to say something to finish, and then, sorry, then question. Just because I think this is very important, and people do it differently. I don't want to say wrong, but I don't like it when they do it like this, which is the threshold. Okay. The threshold needs to be set. You need to set the threshold before training your model. Okay? This is important. Either that or you set your threshold using your training data. Okay? When you, I don't know if you have seen, we don't have time for that, but just just so that you see what I'm talking about, and it's faster and quicker to explain. So if you have seen the ROC curves, so receiving operating characteristics, it's basically telling you what this is doing is trying every single possible threshold and seeing how that threshold ends up with different false positive rates and true positive rates, okay? Accuracies. Let's talk about accuracies, okay? So for example, in my case, I know that the output of my network is always going to be between 0 and 1. Then what I will do is I move the threshold between 0 and 1, maybe steps of 0.1, 0.1, 0.2, 0.3, 0.4, and I see what happens when I apply that threshold to the output of my new network, and then I see, you know, what is the accuracy then? So that will be, it will be different. So if I just change this, I'm going to test this, and instead of 0.5 is 0.1, then now my success rate is 87.2%, so it's worse, okay? So then that's the way it works, basically. I try different values, and then I plot the values, and I say, oh, actually, the best one is this, okay? But think about what we're doing here. we are modifying a parameter of my model, which is the threshold, based on my testing samples. And we said that you should never do, never. So it's okay to do it, to plot the rock curve and to see this is how my model will, works, how stable it is. Ideally, you want that rock curve to be in a certain way so that, small changes in the threshold doesn't have big impact in accuracy, right? Because that means that the model is stable, okay? But when you're going to report your accuracy, you have to use a threshold that is set beforehand or that you have set using the training sample. Very quickly, for example, if you split the training data in two, training and validation, for example, that is called training, and now you have training, validation, and testing, okay? But the validation comes out of your training allowance, so to speak, okay? So then you have kept out of the training a small sample of your training set, and now I'm going to use that to calculate this rock curve and trying to calculate the best threshold. Happy days. Why? Because I'm not using the data that I am going to use later for testing, okay? It may be the case, in fact, that that threshold is not the optimal for my testing samples, but if you want to do that, happy days, okay? Maybe if you have a lot of data, you can do that. But again, just to reiterate, never, ever, ever set any parameter on any model that you use in machine learning using testing data. Never. Not even feature selection. Nothing. Okay? Questions? Sorry, I have run over for 20 minutes. Any questions? No? Okay. Are you sure you don't have any questions? If you want also, because I understand that you guys want to leave. If you want to ask me questions later, you can send me an email. I'm going to write in the chat my email. I think it's in the slides, but just in case. Okay. Just one more thing that I would like to say before going away, and maybe this is the most important point that I hope to imprint on you guys, other than the fact that you never use testing samples for setting any parameter. So, in the context of health, which is where we are at the moment, right? In the context of maybe diagnostic applications, tools for clinicians, etc., etc. When you are building a machine learning model, the most important thing for you is not the performance of that model. It's not how well it works. The most important thing is that it makes sense clinically. Without that, forget it. No one is going to use it. No one is going to, no one important is going to use it. No one important is going to like it. And what I mean by no one important is clinicians. If I throw to a model everything under the sun in terms of variables, I can tell you it will be able to differentiate anything, absolutely anything, even if it doesn't make sense. And I have an anecdote of that, is that I remember we were trying, it was a model with like a gazillion parameters, and then it applied like a kernel that we call like an explosive kernel, because if you started with 1,000 inputs, you will end up with 1,000,000, and then it will go down to 1,000, something like that. So it was, it calculated a lot of stuff. And we actually mislabeled the data that we used for training and testing. And in that mislabeling, we actually were splitting one class in two. So they were the same class, but we were telling the model that they were two different classes. And it was actually able to differentiate between those two different classes when they were actually the same class. So that actually doesn't make any sense at all. So what that is telling us is that yes, numerically, the model can perform really well, but it doesn't mean that what it's doing makes sense. And this is maybe the biggest barrier that machine learning has in healthcare. And again, when I'm building this, I will love that the best performance I have is with the fanciest model, but that's not always the case. And in any case, the performance I have is secondary. The first thing is that it makes sense clinically. So I have to, and this is a barrier for us because of that black box issue, I have to find ways to try to see what's going on under the hood if I'm using artificial neural networks, at least a little bit. And then so that I can tell clinicians, hopefully working with me in that project, I can show to them, this is what the model is doing. Does it make sense? Yes, happy days. No, it doesn't make sense that it's using whether you are vaccinated or not against whatever, COVID, to guess, I don't know, if you have eyesight problems. I don't know. So I'm trying to think of two completely unrelated things. Okay. Okay. One true example. If there is a correlation between ice cream, how much ice cream is sold in a region, and violence. So you can tell, ice cream makes people violent. Stop selling ice cream. Not true. Actually, hot weather makes people violent, apparently, for some reason. And then when it's hot, people buy more ice cream. Okay, so this is the kind of things that you need to unpick. So always, first and foremost, clinically relevant. That's all from me. Any questions or comments? Very welcome. Criticisms of the way we have gone through on Zoom. Aaron, sorry, yeah, someone was going to say something or ask something.
First, I'd like to say, oh, sorry, you talked to me, Marcos.
I think someone was going to say something, Aaron, maybe. I think someone unmuted.
Okay, yeah, see what they have to say.
Yeah, it's just been a lot today, that's all I was going to say.
Yeah, it is a lot. I agree with you 100%. I think you can have probably, and then Aaron, I think, will agree with me, we can have a master's only with machine learning, right, Aaron?
No.
I mean, there is enough material to cover to fill in a whole master, I think.
I mean, I'm trying to cover deep learning in one day tomorrow, and that in itself is. But we have the benefit that you've given a really nice introduction to neural networks, so I can hit the ground running. So I want to say thank you for this session, Marcos. I think you've gone into more detail than I've seen anybody go into detail with neural nets. So yeah, that's great.
Aaron, before we close out, one question.
Yep.
So whatever you have written the code, there is any package where we can directly give inputs for all the training part, everything? Is there any package, or we have to write it manually? Okay,
yeah, so there is I think there are packages of neural networks pretty much in every language. I usually use Python, but in R, I think, so for example, in R, I think it's called Caret or whatever you pronounce it. Well, actually, it's called neural net. That applies neural networks, and you can combine neural net with Caret to do different things. So that's something that I had prepared for the evaluation thing, but we didn't have time. I guess, Aaron, you will go over evaluation, or I don't know. We didn't really. Oh.
So we did went over Caret yesterday, and we did SVM, and there's probably a few different implementations. I think the E1071 and the neural net libraries, they both have a wrapper in Caret.
Cool.
So Marcos, can I get this code in let's say that neural net, how it is done?
Say again.
The code.
Can you?
Give me a minute.
So this code is up on both Canvas, and I've turned this code into a notebook on the Kaggle page as well.
No. I did not ask for the Kaggle one. I was just saying that I need that in, let's say, using neural net package. Like, can we shorten the length of the code? It is too huge. Is there any other way to write it in a shorter way?
So, Marcos has done two things. He's given you this code, which is on right now, which will show you how to run neural networks with Caret, E1071, and the neural network library. But also, just for you to learn, he's given you a manual implementation of neural networks. So you can go, line by line and see exactly what's in the algorithm. That's something that you lose when you just wrap something up in Caret. So I think in practice, you wouldn't really. Well, I don't know actually, because it'll probably be faster to do it manually and do it in something like C++. But yeah, you've got two versions there.
Yeah.
Okay, that helps a lot.
Okay, so any questions before we go, or are we all good?
I was just to reiterate again, feel free to email me if you want to ask any questions outside of this. As you can see, very passionate about this. So I'm more than happy to have a chat with any of you through email or maybe through Zoom if it's better. So again, if you want to know more, please do let me know.
Just a quick question then. It's slightly off topic, I suppose. You said that if you were to do like neural networks and stuff like that, you're more likely to go to Python. Even when you go to Python, would you use a library or would you still program it from scratch?
I use a library. Personally, I'll use a library. It's what Aaron said really about, unless you're trying to do a final application that is going to be deployed, let's say in the NHS or whatever, where you really need it to run super fast and you need to optimize every small detail, then you will maybe write it in C or C++ or whatever. If not, just use a library, especially for research. Don't spend time on building something that already exists. Especially with the one, I don't know if it was you mentioned, TensorFlow, that has a lot of functionality already implemented, and it will make things so much easier. And PyTorch as well, that's the one I use, but either one, it's a good one. And there are more. I think it's one called Cafe, also in Python. Even C++ probably will have. I mean, I haven't used C++ for this, but I guess there will be some neural network library in C++ as well.
Awesome, thank you.
And even, sorry, very quickly, even for TensorFlow and even for PyTorch, they also have already implemented ways for you to run it in GPUs. So yes, it's not going to be the fastest thing in the world compared to, or at least it's not going to be faster than implementing it yourself from scratch in, let's say, C or C++, but it's still going to run pretty fast, especially if you have a good GPU.
Cool. Thank you.
Okay, well, thank you again, Marcos. And yeah, so just for tomorrow, same as usual, any questions between 9 and 9:30, I will try and answer them as well as Marcos has been answering your questions. And we're going to look at convolutional neural networks and recurrent neural networks tomorrow. So I will see you then.
Just one quick question. When will the assignments be released?
Tomorrow at the end of the day. I'll spend maybe 20 minutes just talking about it.
Okay, thank you.
Okay, cheers guys. See you tomorrow.
Bye all.